This is a tutorial about 3D deep learning. And we're witnessing the rising popularity of 3D vision as CVPR. So for this tutorial, we're going to introduce some of the latest progress of how to apply the deep learning techniques with the new coming large 3D data. My name is Hao Su. I'm a new professor at UC San Diego. And this tutorial is co-organized with my colleagues, Professor Guibas from Stanford, Michael Bronstein, Evangelos, Jimei, Charles, and Qixing. Okay. We are going to cover the whole afternoon for the topic of 3D deep learning. And you see that there will be an opening remark for 10 minutes, and then there will be 3 main topics of how to apply deep learning on 3 different types of 3D data. I'm going to first give an overview of the background why there's a new field of 3D deep learning. Okay. And in fact, before talking about 3D deep learning, let me say that we're deeply interested in understanding the 3D because our world around us is composed of 3D geometry, like from the houses we live to the cars we drive, and from the food we eat to the clothes we wear. So we need to understand geometry, we need to understand 3D. And 3D has very broad applications like in robotics, or augmented reality, or autonomous driving, or medical imaging. Sorry. Okay, maybe I should stay a little bit away. Hello? Okay, I think this is good now. Okay, sorry. Yes, so for you who are here, I guess I don't need to say much about why 3D is important. However, historically, most 3D visual computing techniques focused on single models and lacked robustness. In fact, one reason is there lacks the big 3D data. Like there's the famous, in the computer graphics field, there's the famous Stanford bunny and Utah teapot. And in fact, also in vision, in graphics, there has been the shape benchmark, the Princeton shape benchmark. It's been used many years. But the scale is not large and diversity is not sufficient. And recently, we're witnessing the rise of internet 3D models. Like there, you can find millions of models from the man-made models, the CAN models from the online repositories. But also, this is backed by the growth market of crowdsourcing for 3D modeling. And we're seeing, this is the opportunity of data-driven 3D visual computing. We're seeing more and more 3D sensors as well, like for the Connect, for the real sense, for more and more 3D sensors from Google, from many other companies. They are at higher and higher quality, but lower and lower price. It's estimated that worldwide there are over 30 million units deployed, and we can anticipate how much 3D data we will have in the future. So with this background of a big 3D data emerging, there comes the new field of 3D deep learning. It's arguably started from the year 2015 with some seminal works and some big shape data sets. And it's actually very active due to very huge industry interest. But let's say, what are the basic tasks of 3D deep learning? My classification is that there are 3 basic categories of tasks, like 3D geometry analysis, and 3D assisted image analysis, and 3D synthesis. So what are they concretely? For 3D geometry analysis, these are a number of exemplar tasks, like 3D classification. Given some 3D object, maybe it's a volume, maybe some other form, what's the object? Or 3D parsing, given the 3D object, what's the part of it? Or give a scene, what the objects constitute it? And there's the correspondence problem. Try to build a point-wise or part-wise correspondence across shapes. And also, the second type, a main type of 3D deep learning task is 3D synthesis. Like you may want to build a 3D model out of a single image, or you may want to complete a partial scanning, or you may want to do the image or modeling based upon other constraints. A third category is the 3D assisted image analysis. Like if you have the image as the query, you want to retrieve 3D models, which might be a cross-view. We see many of these kind of tasks, cross-view image generation, or intrinsic decomposition, many of these kind of problems. Okay, 3D is not explicitly used, but somehow it's in between. So from the network perspective, we see that we are designing the networks for 3D as input, as output, or as intermediate latent space. And for the sake of time, for this tutorial, we'll focus on two types of applications, the 3D geometry analysis and 3D synthesis. So I'm presenting one dimension of the 3D deep learning categorization, like in terms of tasks. But a second issue that I want to mention is that there has been a number of new 3D deep learning algorithms. That's like, because the 3D deep learning has different kind of fundamental issues compared with the 2D deep learning techniques. Like for the image case, basically we assume that our input is 2D regular grids, okay? And images has the unique representation that it can be represented as 2D array of pixels. Somehow for this regular structure, it admits the convolution operation. But on 3D, this is very different. There are so many different representations of 3D, each tailored for their own application scenario. Like, I'm listing a number of the popular ones. The multi-view representation. For one object, you look from different viewpoints. It might be RGB or RGBD. A volumetric. This is more in the medical imaging society, but also you can also try to volumize other types of 3D data. Like you have the regular grids, you use the distance field or some other kind of a field-based representation. Or a polygonal mesh, a 3D model is represented as a collection of triangles or other kind of polygons. A point cloud, so for 3D data, you have a set of points, which might be unordered. And this is a very common type of 3D data from the raw sensors. Or primitive-based CAD models. Your CAD model is made of a number of primitives. Each might also have its own control points and other kind of a parametric representation. So in general, we can classify the 3D data into two types of representations. The rasterized form, which has a regular grid structure, and the geometric form, which is often irregular. So from this perspective, we can classify, there's a different dimension to classify the 3D deep learning algorithms. Like there are the algorithms for multi-view representation, volumetric representation, or in point cloud, the mesh and part-based representations. Historically, because of the similarity to the images, the multi-view and the volumetric CNN kind of started earlier. But within this year and last year, actually, we're witnessing more deep learning work on other types of irregular 3D representations. And we see a number in this CVPR. Okay, so the task space and representation space builds the Cartesian, there's the Cartesian product of the two that builds a very rich space to explore for 3D deep learning. And basically, for our tutorial, it will be organized along the representation dimension. But for every representation, we're also going to introduce the networks for different tasks. Okay, I've introduced before. There's the fundamental challenge of 3D deep learning. Like for images, you can it has a regular structure, and you can use the convolution on top of it. But for the 3D data, there are the rasterized form, as I just introduced. And basically, you can try to directly borrow the convolutional neural networks from the image analysis field. But it will face a number of other challenges, and you'll see that from the tutorial. And also, there are the irregular representations that you cannot directly apply CNN to it, but we have to invent new types of deep learning architectures. So that basically finished my overview of the 3D deep learning field. In the rest, we're going to listen to the our lecturer's talk on specific types of 3D deep learning representations. Sorry, deep learning on different 3D representations. Like we'll proceed in this order. Sorry, the first one is the deep learning on regular structures. Okay, the second one would be the deep learning on point cloud and the parametric models. Sorry, we switched the order of second and third because our presenters' time schedule. And lastly, we'll give the introduction to the deep learning on matches, which is kind of the graph structure. Okay, so thank you very much for coming here, and let's welcome our first speaker to introduce the deep learning on regular data.
1, 2. Yeah.
Full screen? Control L.
That was the.
Here it is. Okay. Well, thank you, Hao, for organizing this. I'm Evangelos Kalogerakis from UMass, and I will discuss, first of all, the multi-view representations for 3D shape analysis and synthesis. So, starting with the multi-view representations, I'd like to say, first of all, the basic idea is to take a geometric representation of 3D shapes, such as the polygon mesh or a point cloud, and convert it basically to rendered views of this 3D representation. So we produce 2D images where we can apply the traditional image-based convolution or apply image-based architectures that have been used a lot in image-based analysis. So geometric representations in general can have various artifacts. For example, if you take, for example, the chair that you see on the right and zoom in at the chair, zoom in at the leg of the chair, you'll see that the parts are disconnected. Now, if you take this 3D shape and render it, produce images out of this 3D shape, you'll see that the images do not incorporate this kind of difference. Visually, it's barely noticeable. So image-based networks will not be affected by this kind of artifacts. Geometrically, however, there are severe implications in the manifoldness. The geometry becomes non-manifold. There is implications of the topology changes. So geometrically, there are various implications that can affect the performance of a network that operates purely on geometry. So the view-based representations try to circumvent this problem by converting essentially these geometric data structures, polygon meshes, point clouds, to images. And also a good thing about doing this conversion is that essentially if you take a polygon mesh, well, a polygon mesh is a set of vertices connected with edges that form polygons. I mean, every vertex can have different number of neighbors, every face can have different number of neighbors. The tessellation can be quite irregular, so you cannot also order the vertices. The neighboring vertices for each vertex, you cannot create a nice ordering of the neighborhood around each vertex. So convolution is not trivial to implement in this kind of data structures. So by converting everything to images, by converting everything to regular grids, you can apply your traditional convolution. So essentially, the advantage that you get directly by doing this conversion is that you escape from geometric artifacts. The representations like polygon meshes have artifacts commonly, like non-manifold geometry, irregular tessellation, parts that are disconnected. So the rendered images will not be affected by this kind of tessellation artifacts, or will be minimally affected. Another big advantage of view-based representation is that you can leverage existing image-based networks. You can take essentially your favorite network that was trained on massive image datasets like ImageNet, and you can apply it actually for 3D shape analysis. I'll show later that this actually works. And this means that you can take the advantage, the best of both worlds of combining images and 3D shapes. So the more data, the better for deep learning. So image-based architectures have this kind of advantage. And also, I would like to mention that this is somewhat, the view-based representations are somewhat motivated by human vision. I don't want to say that we are inspired by human vision because nobody knows exactly how human vision works, but essentially we can recognize that a chair is a chair by just looking at it, by a particular view. We analyze what we see. We don't see the interior of the shape. I mean, we can infer that the shape is a chair just by looking at the surface of it, a particular view. And if we want, we can take many particular different other views and infer that you have a chair. So basically, view-based representations are working somewhat like this. You just take multiple views of the 3D shape, you combine information, aggregate information from different views, and you can basically recognize that you have a 3D chair. So somewhat it's motivated by, let's say, human vision, although it doesn't work necessarily like human vision. Another quick remark is that 3D models, like the ones that you have in computer graphics, they're empty inside. So if you take, for example, the chair on the left and check what happens inside, you'll see that the interior is empty, which means that, well, maybe you don't want to spend representation power to go with the shape interior. And view-based representations are basically analyze the surface, the rendered views of the surface, so they don't spend representation power on the interior. They just focus all their representation power on the surface. So let me proceed by explaining the multi-view CNN architecture for classification. This is essentially the view-based CNN 1.0. So the goal here is to perform a classification given an input geometric representation like the chair that you see here. We want to recognize that it's actually a chair. We want to basically, from all possible candidate classes, to infer that this is the most likely chair based on the input geometric representation. And here, the idea is to take essentially the input 3D shape and render it from multi-views. So in the first version of the view-based CNN, what we did is to place cameras around the 3D shapes. If the shape was upright oriented, we were placing 12 cameras looking at the center of the shape, elevated slightly from the ground, looking down towards the shape. And the rendering, how it was done, was passing essentially your polygon mesh through your GPU that is capable of doing very fast rasterization, find all the pixels that are painted essentially by your polygon mesh. And what you're producing are rendered images that have essentially this kind of shading effects that you can see on the right. So these renderings can be produced by taking the surface normal and dot product it with the view vector. So it's an encoding of the surface normal relative to the view direction. So what you can do with these rendered images? Well, you can design basically an image-based architecture that processes these images and outputs a single descriptor. You want to produce a single compact descriptor from all these images. You don't want to compute a different descriptor for every different view, because when you compare shapes, it would entail comparing all possible view descriptors with all the other view descriptors and this from the other shape, and this means that you would have a quadratic explosion. So you want to produce out of it, out of all these views, a single nice compact representation. So in order to do this, let me explain what happens inside this view-based architecture. So you take, let's say, the first image, the first render view, and you pass it through your favorite image-based CNN. This could be AlexNet, this could be ResNet, it could be VGGM, like what we did in the first implementation of this view-based network. So you get essentially the feature maps. You can get the feature maps up, for example, Con5. So the Con5, the fifth convolution layer, will produce, in the particular case of the VGGM, 256 feature maps of size 4x4. That's what the first view produces. And the second view will also pass through your image-based architecture through VGGM. It will produce another set of 256 feature maps of size 4x4, and from the third view and the fourth view and so on. So the trick here is to take these feature representations and concatenate them into a single descriptor. So what we do is to introduce a special layer that we call view pooling layer, and what it does is the following. Let's say that the first feature map, the first filter in this Con5 encodes the chairness of the image. It's not necessarily the chairness, could be really anything, but we have seen basically that image-based architectures, when they are trained, they're sensitive to particular parts or objects in the input image, like then encode dog faces, cats, chairs, legs, and so on. So let's say that the first view produces in the first, from the first filter, an activation of 8.0 for chairness. You go to the second view and you see that the chairness is 1.0. The third view is 0.0. Maybe there is no chair in the well recognized in the third view. And you go to all the views and you take the maximum of these activations across the views. So you get the number 8.0. So you use essentially the view that is most informative about a particular kind of feature, like chairness. And you do the same for the second feature map, the third feature map. Essentially, you get an element-wise max operation across multi-views, which can be implemented very easily in terms of implementation. You can go to Café and you access you see the L2-wise layer that does this element-wise aggregation. So now that you have essentially your resulting aggregated representation, it's 256 maps of size 4 by 4. You can go on and process them through the rest of the layers of your favorite image-based architecture, like the FC6 and the FC7 layer and so on. You can take essentially your layers from your favorite image-based architecture and process these feature maps to output essentially a descriptor. And this descriptor can be mapped to probabilities. For example, you can basically decide that, well, based on this descriptor, based on a linear classifier, that this is shared with this certain probability. Now, a key thing here is that you don't take all these filters, all these layers, and train them from scratch. An important thing here is that, while optimization in neural networks is kind of hard, you can have many local minima, but the more data you have, the better. And essentially here, you can basically go to the image-based architectures, and you can see that if you pass rendered images of shapes, they're still going to recognize your 3D shape. They can still basically output with high confidence that, well, this is a chair. So why not use pre-trained networks? I mean, trained on massive image data sets. The more data, the better. If you have more data, it's more likely that you're going to converge the better local minimum. So the idea here is you take your network, your VGGM or AlexNet, pre-train it on ImageNet, and now that you pre-train it, you go and fine-tune it, change a bit the parameters. It's crucial to change the parameters in the last layers especially, so that it performs well for shape classification. So that's the whole idea. It's a form of transfer learning essentially that can work well in practice. And what we did in the very first implementation is to use the VGGM architecture to do this, all convnet layers, both from the part on the left and also on the part on the right, where including the FC layers, were initialized from an architecture that was pre-trained on ImageNet. Okay, and all we did was fine-tuning in the case of 3D shape classification. Backpropagation can be implemented. The view pooling layer is differentiable. You can push the gradient all the way from the last layer back to all the FCN, back to the all image-based branches that you have on the left, so you can implement backpropagation. Now, an important thing here is that all the branches that you see on the left, all the image-based branches, all the first 5 convolution layers are sharing parameters. They are sharing the same filters. And the reason for this is that the 3D shape can be oriented in a different manner, so the views are exactly not ordered. They're unordered. They can, you can have a chair where the first view is basically looking at the chair from this side kind of viewpoint, but you may have another chair that is oriented in a different manner, and the first view would be something else. So the views are not oriented in a particular manner. That's why all the branches should share the same parameters. In the end, you get a descriptor. You can perform classification through this 4096 descriptor that comes from the last fully connected layer through a linear classifier. And alternatively, what you can do is, for the case of retrieval, you can take this 4096 descriptor, let's say descriptor X, you can pass it through a linear transformation layer like W.X, and reduce its dimensionality to 128. That's what we did for the case of retrieval. So we trained for this matrix W that performs this dimensionality reduction so that shapes from the same class have similar descriptors, otherwise different descriptors. So in this manner also you can achieve better performance for retrieval. So when we initially implemented this version 1.0 architecture, we saw an interesting thing, that even if you take an image-based CNN, even without fine-tuning, it was performing already much better compared to the first version of volumetric networks, both in terms of classification accuracy and retrieval. So an image-based CNN, even without fine-tuning, it can work well. If you do fine-tuning on top of this, you can get better, slightly better classification performance, and especially you can get much better retrieval performance, as you can see in the red, in the numbers with red color here. So it was working pretty well. We're pretty excited about view-based representations from this aspect. Also, if you go and check which pixels are more important for determining the output probabilities for the ground truth class, this can be done by just examining the derivative of the output scores, the output probabilities for the ground truth class with respect to the image, the input images. You'll see that the pixels that are more important for determining the class are the ones that are lying on the silhouette or near the internal feature curves, internal contours, like suggestive contours, ridges and valleys of the 3D shape. So this also agrees with remarks that have been done in the non-photorealistic rendering, artistic rendering community that says that while internal contours like ridges, valleys, suggestive contours are important for perception, for the perception of shape. So you get some kind of approximation of this kind of contours in a very fuzzy manner by doing this examination of the gradients. So then the people from Stanford came and said that, well, if you can render your 3D shape through spheres at multiple resolutions, you can also gain a bit better performance. You can also use AlexNet, and this provides a couple of % more accuracy in ModelNet 40. So by then, we had basically state-of-the-art performance in 3D shape classification, and while during the recent years there have been changes, the gap between volumetric methods and view-based methods have closed. Still, we don't know which one is the best method because everybody employs different architectural tricks, and it's not clear what is performing best, but essentially the view-based methods are offering already very, very high performance. Now, a problem with that exists in the current architecture is that if you see the viewpoint selection procedure, before it was fixed, we just placed 12 cameras. You can do something smarter so that you avoid surface information loss. You want to capture the whole surface so that you don't miss any important regions. So I will just explain the view based in an architecture 1.1 in the context of segmentation. Here the goal is to basically segment the 3D shape into labeled parts and to have human annotations of labeled parts already in ShapeNet. And what we did is essentially design an architecture that takes as input a geometric representation of a 3D shape, renders the shape into multiple views, and outputs segmentation labels, a discrete label for every polygon on your polygon mesh, which entails essentially creating a segmentation and the labeling of the input surface. So what we did here is to take the input shape that you see here as blue, and first of all, for a particular distance from the surface, infer a set of cameras that maximally cover the surface area. So we place the first viewpoint so that it covers most of the surface. We mark this surface as covered, and then we go and find the second viewpoint that covers most of the so far uncovered region. And we do this over and over again until we find the viewpoints that cover 99.9% of the surface. And we do this at a different camera distance. We place also cameras farther away and farther away, doing exactly the same greedy procedure of selecting cameras so that we capture the surface at multiple scales. So that's one important difference with the previous architecture, that we do some kind of adaptive view selection per input shape. The second difference is that we render both shaded images, so surface normal dot view vector, and we also render depth images that encode surface positions relative to the camera. And now all these pairs of depth and shaded images are concatenated into two-channel images, and they pass through fully convolutional networks. The fully convolutional networks will output for each view confidence maps. So we produce a confidence map for each part label and for each view. For example, here on the top, on the first branch, you'll see that we produce the confidences for wings, for the label wing. So the redder the value, the higher the confidence the particular FCN branch has for detecting wings in this particular view. And we do the same from the second, the third, and so on view. So we have all these branches that produce confidence maps for each part label. Now, again, these confidences live in image space, and we have to aggregate all these onto the surface. So what we did is implement a projection layer, which was inspired by the previous view pooling layer that we had in the previous architecture. What we're essentially doing is that for every triangle on the surface, we find all the pixels that were rasterized, were painted, in other words, by that triangle. We access their confidence values, and we use the maximum of these confidences. In other words, if in a particular view we find that a wing exists with very high confidence, well, we use this confidence, we project this confidence onto the surface. And we do the same procedure for each part label. We aggregate all these based confidences and project them onto the surface, so we get a surface signal, which is essentially the confidence for each part label. Now, the last and another important difference with respect to the previous architecture is that the confidences that we get through this view pooling procedure might not be perfect. There might be 0.1% of the surface that was not viewed by any viewpoints. So we need to propagate confidences to these areas. We want to produce a coherent labeling throughout the surface. So we have a surface-based model here to correct basically things and propagate confidences to regions that were invisible. So we have a surface-based model which has the form of a condition random field. It has unary terms which are based on the confidences that were extracted from the projection layer, and pairwise term that favor the similar label, similar confidences, essentially for neighboring faces that have similar normals and different labels otherwise. And essentially how it works is essentially to diffuse essentially the confidences through inference in this probabilistic model so that you correct any inconsistencies that were produced by the view-based nets. And this whole thing now, all the architecture, including the FCN branches that share parameters like before, and the CRF parameters are trained jointly. You can basically derive gradients analytically. All the layers are differentiable. You can backpropagate gradients from the CRF to the FCN branches, and you can train them together. So what we see here is a marriage between the view-based model and the surface-based model to get the best, let's say, of the both worlds. Any FCN module can be used here. I mean, we used the architecture back from Long and Dahl, the first FCN architecture, but in general, you can use many different architectures. For example, someone can use the most recent architecture, which is the so-called UNet, which basically composed of an encoder. It takes the input image and encodes it into a compact representation in a small feature map, and then deconvolves it through upsampling to confidence maps for each label. And the trick here is that you can take the encoder representations and concatenate them through with the decoder, and this gives very good performance in image-to-image translation tasks. So in general, you can use any FCN modules. Of course, the more advanced the FCN module you have, the better. And I think the UNet would be a better alternative to what we implemented. So if we see what is created from the labeling that is created just by using the FCNs, just by projecting the confidences to the surface without the CRF, we'll see that there will be some inconsistencies. You will see some blue areas in the area of the frame of the motorbike, some tiny areas that were not visible by any views, this 1% of the surface, that is corrected essentially by doing inference on the CRF and do the diffusion so that through the inference, the mean field inference that we're using in the CRF, you produce essentially a much more coherent and correct labeling that agrees with the ground truth much more. So what we see here is in the version 1.1, to summarize, viewpoint selection, which is adaptive per se to minimize surface information loss, the marriage of the FCNs, the image-based networks, with a surface-based model, which offers good labeling accuracy. Right now, we don't know which method is the best because everybody is using its own splits in ShapeNet, so it's not very clear. There are challenges. View-based networks, the FCN branches that we saw before do not process invisible points. These need to be treated by the surface model. The view-based representations have redundancy, so two views that are nearby will basically process a large common area of the surface at the same time. So the surface is processed multiple times by nearby viewpoints, so there is some redundancy, which might be good actually if you have noise, but whatever. It's slow to train. These image-based networks are huge. They were developed for classification of in ImageNet for 1,000 classes. Many filters here will be permanently inactive because they were basically designed for classification in classes that do not exist in ShapeNet. So the number of parameters is here huge. That's why they're very slow to train. Yet I believe that one can basically try to distill or to shrink, compress essentially these networks for the case of shape analysis, since many filters are not particularly useful. And aggregating view representations via these view pooling layers, this max pooling, might lose some information. We experimented here with other options like LSTMs, combining essentially aggregating aggregating surface information across multiple views through RNNs and LSTMs and gated recurrent units, but we actually didn't see any improvement compared to the max pooling. It seems that the max view pooling is quite powerful. Very briefly, I will mention that this view kind of Bayes architecture can be used for finding correspondences between 3D shapes. If you have a point, you can produce a descriptor through a view-based architecture. You take a point and you find essentially views that access the neighborhood of this point. The point is not occluded by the views that you need to select. You take all these images from this viewpoint configuration, you pass them through your favorite image-based architecture like AlexNet, you pull out the descriptor, and you want to train your architecture so that points that are in correspondence have similar descriptors, otherwise they should have different descriptors. So you use the so-called contrastive loss. And the good thing here is that you can get essentially from human annotations of parts, you can get the parts, perform a non-rigid alignment procedure so that you find correspondences, and you can use this for training this architecture. So you can get basically training data of correspondences for free, for almost free, given the human annotations of parts. We saw actually that this method, even if it's trained on synthetic correspondences, it can generalize to correspondences between 3D models and scans. So here one column shows 3D models on the left, and the next column shows scans with noise and missing regions, and the same thing happens for the second and the third column. You'll see that essentially you can find correspondences between scans and 3D meshes. Here, similar color corresponds to points with similar descriptors. So we saw that you can build matches basically between scans and 3D shapes, and actually compared to volumetric approaches in benchmarks of man-made shapes, we saw that you get much better performance compared to 3D mats. That's what I want to mention very briefly about correspondences. Finally, last thing is we try to squeeze in UMass every bit of juice out of the view-based CNNs. We also use them for synthesis. So here you see two input sketches, so two input line drawings that were drawn by humans. And the goal here is to get a 3D model out of these sketches. It's very common in graphics to prototype with sketches, and you want to get a 3D model out of it. So we had an architecture that takes the input sketches and codes them into a feature representation, and then decodes them into normal and depth maps for different viewpoints. So we had the decoder that outputs depth and normal maps for a particular viewpoint, then a second branch, a third branch, up to 12 branches that produce depth and normal maps. And we also had the GAN, we had the discriminator that tell you during training whether you are good or bad, whether you are fake or real. This is common now in generative models to have this conditional GAN kind of architecture. Now we change it so that it's adapted in the view-based setting. So we had training data. I mean, you can produce synthetic line drawings based on standard artistic rendering, non-photorealistic rendering algorithms, and you can get pairs of synthetic line drawings with depth and normal maps from different views. So the thing here is that during training, if you have a 3D model, the depth and the normal maps that you get are consistent because they correspond to a ground truth 3D model. During testing, however, there might not be such consistency. There might be some discrepancies between the different depth maps. So what we had is an optimization, a fusion strategy. So what it does essentially, briefly, I would mention that essentially you take the depth maps and the normal maps. You want to ensure that the depth and the normal maps agree. So you solve an optimization problem where the depths are unknown. You want the depths that will be optimized for to be as close as possible to the predicted maps, and at the same time you want the derivatives of the depth that approximate tangent directions of the surface to be as orthogonal as possible to the predicted normals. So you try to fuse essentially information from both depths and normals, and we found that this is useful. Another thing which is even more important is to take essentially the depth of a point at one view, grab the 3D point by essentially inverting the orthographic projection that you used. From the view, you can go back to the point cloud and then project this point back to another viewpoint. Now, you want to make sure that the resulting depth of this 3D point that you get with respect to another viewpoint agrees with the depth that you predicted for for that viewpoint from your net. So you have essentially a problem that you want to fuse all the depth maps and the normal maps all together in optimization and strategy to produce a consistent point cloud from all these views. Then you perform essentially surface reconstruction through your favorite point cloud to mesh conversion technique. And then optionally, what you can do is to fine-tune your surface. You can essentially take your polygon mesh and deform it so that it matches more accurately with the input contours. This is happening because essentially all generative models right now for images and surfaces tend to lose details. You saw basically an image or a 3D shape to someone from the vision community. He's very happy. You saw the same image and the same mesh to someone from the graphics community and says, oh, this is horrible. You will lose basically all the details. So, well, for satisfying also the graphics community, we have essentially this fine-tuning procedure for deforming the surface so that it agrees with the input contours. And in general, I think that generative models for 3D surfaces based on deep learning is something that it's an open problem, especially for generating details. Compared to alternatives like volumetric methods, I mean, here you see the reference shape and the line drawings of this 3D shape. You want to create reconstructions that mimic as much as possible the reference shape. We saw that our method called shape MVD is much better to volumetric kind of reconstructions, baselines, or better than going to the database and performing nearest retrieval. We saw this especially in terms of preserving regular structures and topology of the 3D shape, especially you see on the right, we can recover correctly the structure on the back, while other methods don't. And we saw this for characters. We saw that you can recover somewhat a bit better detail compared to other alternative methods. It works also for characters. It can work for a single sketch or multiple sketches. Of course, providing multiple sketches is a bit better because you have more information in multiple sketches. If you draw from the front or the side, you want to use this information from both sketches. Well, this fusion process that I described before, disadvantage of this pipeline is right now that the fusion, this optimization is outside the network, so it's not an end-to-end network like the previous ones that I discussed, so this is an open problem. And another issue is that, well, with view-based representations, you cannot see through the surface. As I said, we do not want to encode the interior, which might be seen as an advantage or might be seen as a disadvantage, especially if you have some volumetric information, some information inside in other applications. Finally, there is, as I said, some redundancy in the view-based representations. Different views might capture the same surface information, and this might not be necessarily consistent. So this is something that to think about with respect to view-based representations. So the alternatives, the volumetric representation. I didn't have a timer here, so I might have taken too much time. So, Jimei, you're next, or you want me to go over? Here. Well, do you want me to go over the first slides, or are you going to go over it? You want me to go over it? Okay, go.
Hello, everyone. My name is Jimei from Adobe Research. In the following, I'm going to review this deep learning volumetric representation. So there's so many work recently on this topic. So I'm going to not give a comprehensive overview of all the literatures, but focus on some key ideas, how we can do deep learning on volumetric representations. Just a second. It's not responsive. Okay, some technical issue. So there's many kind of volumetric data in the world, so especially from scientific domain. You see, we have fMRI, CT scan from medical imaging, and also some like manufacturing data for shape analysis, and also some scan data for geology. So there's so many kind of this 3D volumetric data. That's really not common to this visual observation of this world. So we know that 3D volume essentially is just a trivial extension to this 2D image data. So given the successful applications of a convolutional network image data, of course, a trivial way to process 3D volumetric data is extends the 2D convolutional network to 3D convolutional network. So the basic concept essentially is 3D convolution using the 4D kernels. So give a look at this example. So given input volume 30 by 30 by 30, we can apply 48 kernels to get this downsampled features. Each of the feature actually is another volume with a size of 13 by 13 by 13. So we can apply this 4D kernel repeatedly to extract a higher level feature on 3D volumetric data, so that we can perform 3D shape analysis and other tasks. So this plain 3D convolution has been adopted for shape analysis in early days for 3D shape classification, for example, on ModelNet 40 and Model 10, this kind of database. So, however, due to these vocalization steps, we look at this teapot. When we convert this cat model to voxelize the occupancy grades, there's a lot of detailed information has been lost. So those voxel-based 3D convolution network cannot achieve comparable result as 2D convolution on views for 3D shape analysis. So the 3D convolution multi-view CNN just like introduced by Evangelos. On the other hand, people also use this 3D convolution to generate volumetric data. Essentially, the core operation is 3D deconvolution using 4D kernels. In this example, given a vector z, we can first convert that to a 4D volume with the number of kernels of 512. And each volume or feature map is 4 by 4 by 4. When we apply 4D kernel and 3D deconvolution, we can get a feature volume 256, and which each of the feature volume A by A by A. So repeatedly, we can generate a voxel 64 by 64 by 64. This way we can generate a lot of shapes. So recent work from MIT published on NIPS 2016, they use this both 3D deconvolution network and then 3D convolution network to generate 3D shapes and for unsupervised learning. So essentially, there's a pair of a 3D convolution network. One is called generator that map the latent code or latent variable to a 3D shape. And then there's another discriminator that can tell whether a generated shape is a realistic shape or not. So this is trained in this famous GAN work, is generated adversarial network. So results pretty amazing. So we can see that the latent vector can capture really some high-level geometry representation of 3D shapes and some styles of the 3D shapes. So they perform this arithmetic operations. So they can generate a new style of 3D shapes. So now I will talk about important application of a 3D data in computer vision. Essentially, is we want to generate or reconstruct 3D shapes from single image as an observation. So previous work focused on depth, but the depth essentially is 2, 4, and 5D representation, not 3D representation for the entire scene. On the other hand, there's a model-based method that cannot be easily generalized across different categories of objects. So let's see how we can use this volumetric representation and the volumetric 3D convolution to reconstruct 3D shapes from single image. This is early attempt from Stanford. So given the image, essentially, there's a 2D convolution network that maps the image into the latent features. And then we can map this latent feature back to a 3D space using a 3D deconvolution network. Just show it here. They also generalize this single image-based 3D reconstruction to multi-view to aggressively absorbing more information from other viewpoint of the 3D shape. Let's look into their network. The image encoder is very simple. Given the image x1, it's just a couple of convolution and downsampling operations. You can learn its latent features, a vector. Here is an essential concept in their paper. It's a 3D convolutional LSTM. It's a recurrent neural network with memory cell. So when we're passing through the image feature from one viewpoint, and then they will be memorized in this recurrent neural network. So when we observe new viewpoints of the 3D shape, and then all the information can be combined together to generate the 3D shape in better and better details. So the feature, or the memorized feature from this convolutional network, and then fed into this 3D deconvolutional network to generate the 3D shape. This operation has been defined in the previous slides. They train this network in supervised way with a ground truth 3D volume. Essentially, are the voxelized 3D shape from these cat models. So here they define this voxel cross entropy loss in this equation. The P index with ijk is the likelihood for the particular voxel of how likely this voxel being occupied. And the Y here is the binary label to tell the ground truth whether this voxel is being occupied or not. So they can easily train this network based on this loss. The data they are using is from ShapeNet. They use a 50K cat model and voxelize it into a 30 by 30 by 30 occupancy grids. And the image is essentially also rendered from those shapes to get this ground truth correspondence for training. So now let's look at some visual results. The first row are the images, and second row are the generated 3D shape. You see, it's pretty impressive. Especially if we have two different kind of views from shape chair, they can generate fairly aligned and similar shapes. Of course, we can notice that you can see this chair, or sorry, this not chair, this table. From this viewpoint, we can generate really good. They can generate really good 3D shapes with 4 legs. Very nice. But these viewpoints convey a lot of detailed 3D information. But at the same time, it's pretty obvious that from this viewpoint, look at the chair, it's pretty ambiguous. We cannot guess how many legs in this table. So this is generated results. Clearly, we miss a lot of legs here. Unfortunate. But this is a pretty common issue. This is 3D basic reconstruction, 3D reconstruction. This is the early attempts. Recently, there's another line of work that tried to combining the 3D voxelized representation and the 2D viewpoints. So they're concerned with another practical scenario that there's no ground truth 3D data available. So how we can train the neural network to generate the 3D shapes from single image. So the core concept in this work, or this line of work, is to implement the 3D projection, or the projection from 3D shape to 2D, given a camera. Let's look at the detail. So essentially the concept is the ray. The image from the camera center passing through the pixels or image plane, reach to the 3D volume and then passing through the volume. So there will be an intersection between this array and the 3D volume that we want to generate. So to get this correspondence from 2D mask, 2D image, and the 3D volume, essentially, we need to find for every pixel of 2D observation, we find the segment or intersection along the ray. So here how this is implemented. So for every pixel on the 2D observation, you can sample points with the disparity, in a range of disparity. So it generates a fake or pseudo 3D points, 3D points. So given the perspective transform, we can apply this inverse transform, perspective transform to generate a sample point on the target volume, so that we can perform bilinear sampling on this target volume to generate another volume, so that we can collapse this warped 3D volume to a 2D masks. This is how we can generate a 2D mask from the 3D shape or 3D volume. This exactly implements the perspective transform or perspective projection from a 3D to 2D, given a camera. So given this perspective transformer layer, so we can define the loss on masks, so that we don't need ground truth 3D volume for supervision to learn 3D reconstruction from single view. So a little bit detail for this network. Same as before, we have an image encoder that maps the image to a latent variable, latent vector. And then given a latent vector, there's a 3D deconvolution network generates 3D shape. And then the key is there's a spatial, the perspective spatial transformer network that project the generated 3D volume to 2D masks. And then, the 2D mask loss applied to these projections. So the overall, the loss can be defined as a combination of the ground truth. Suppose we have the ground truth volume, and this is ground truth volume and the projection mask loss hybrid pattern. So also this network can be trained on the shape nets, some CAD models, voxelized. So given we can see some visual results. Given input image, this is ground truth 3D shapes voxelized from different viewpoints. And this is the results only trained with the view masks, the view loss or projection loss. And this is the trained with the combination loss. This is the result trained with the supervised voxel loss. So we can see only given view as a supervision, the generated shape is pretty close to this supervised voxel loss. So another thing can be noticed that you can sometimes the view-based training can generate even better result than this ground truth voxelized training. So the main intuition, you can see there's a small hole here. So intuition behind this, all the viewpoints in the 2D observation essentially define the compass hall for all the possible 3D shapes. So the network tend to generate a more solid 3D shape instead of holes. But there's always a question here. So since people will ask, given all these 2D observations and the cameras and why not just first reconstruct the 3D shapes and then use the generated 3D shape as supervision to train a network? So these experiments will answer this question. So we designed these following experiments. There are two scenarios. One is for every object, we only allow network to observe a narrow range of views. For example, here only cover 90 degrees. Another scenario is for every object, we only allow network to observe a sparsely sampled viewpoint, so that it's not easy to pre-reconstruct 3D shape for any kind of objects. So surprisingly, we can see from this row, it's only view-based training. This is a partial view training can generate a fairly similar result to this full view training. So you can see this is a narrow view. It's slightly worse than the sparsely sampled views, but it's pretty close to this full view from this 360 degree. So the main intuition behind this is that this encoder-decoder model essentially play a role that can condense all this partial 3D information from different shapes during the training. So there's a concurrent work in this CPR. It's an oral paper. They implement this 3D to 2D projection in different ways. they look at the ray directly, so instead of look at the mask. So they call differentiable ray consistency. Essentially, given a pair of 2D observation and a camera, for any ray emit from the camera center, they want to trace all the voxels on this target volume along this ray. So when they find all those voxels, so they define a new concept called the ray termination probability. So that can determine or build the relationship between the pixel and all the voxels along the ray. So a little bit detail here is to clarify the concept is, intuitive explanation is, suppose we have a ray. If this ray passing through the 3D volume without stopping, that means all the voxels along the ray are likely to be empty. So on the other hand, if this array stopped at a certain voxels, that means the remaining voxels along the ray are likely to be occupied. So this is how they implement this concept called differentiable ray consistency across different viewpoints. So when they build this ray-based relationship between pixels and voxels, they can backprop all this 2D observation information, such as foreground masks, or depth, or color information, or semantic information, even backprop to the 3D volumes for training. So this multi-view-based supervision for single-view-based 3D reconstruction essentially connect these two dots. One is a volumetric representation for deep learning, and it's a multi-view-based representation for deep learning, as just introduced by Evangelos. Okay, as you may notice that all this previous work can only deal with very low resolution 3D volumes. For example, 32 by 32 by 32. It's pretty low dimensional, low resolution. The problem is, you can see from here, this low resolution volume lack a lot of details, and introduce some artifacts. So here, suppose we voxelize this CAD model in different resolution, we can see more and more details are added that can represent exactly the shape of this CAD model. So recently people noticed this issue, and then there's a key characteristic for this volumetric data is their sparsity. So when they increase the resolution of the 3D volumes, you can see very few voxels are actually occupied. So that means if we apply 3D convolution on those voxels, most of the computation are wasted. So how we can deal with that issue so that we can scale up the 3D convolution up to a higher resolution of 3D volumes. So here's the key idea. People adopt this octree structure to represent these 3D volumes through 3D occupancy grids. So the octree essentially is a recursive data structure that partitions the 3D space, partition the 3D space. For every node on the octree, have exactly 8 children or octants. So that's evenly partitioned this voxel in 3 dimensions. Sorry. So of course, given this orientation, we can ignore we can skip many computations that can be wasted before. So in this example, that illustrates a 2D shape from a 3D. So this when we apply regular dense 3D or 2D convolution here on these masks or shapes, you can see every cell here is one kind of multiplication using the kernel. So you can see all those are wasted actually. Only the color pixel here are valid multiplication or convolution to process the data. So if we do have this octree, here is the quad tree actually. So when we partition the space like this way, we can save a lot of computation or multiplications. That essentially gives us the memory efficiency and computation efficiency for speed up or scaling up the deep learning on 3D volumetric data. again, so the key operation on this arbitrary convolution is the convolution itself, of course, and also the pooling similar to convolution. So this recent paper defined convolution on this arbitrary structure to analyze the 3D shapes. So I think I will not talk about details of this representation. There's a lot of mathematical details need to be introduced if we want to understand the concept clearly. But I want to mention one key concept to implement this arbitrary convolution is this neighboring hoods. So because when we store this 3D data in arbitrary structure, then we basically break down the spatial neighborhoods on all the cells. So, but when we perform 3D convolution, we do need this 3D neighborhood structure. How we can do that? In those papers, they basically build a hash table to index all these neighboring hoods when applied to 3D convolution at a certain location. So that's the key ideas applying arbitrary convolution. So that is the result of reports on this 3D shape classification. You can see when they increase the resolution of the 3D volume, they can achieve a comparable result with this 2D-based multi-view convolution network introduced previously by Evangelos. Okay, this is another paper. They are concerned with generating high-resolution 3D shapes. So they also implement arbitrary structure in the deconvolution network, but they introduce a new concept. Essentially, for every voxel, we can look at here, they label this voxel to 3 kind of tag, basically. One is one kind of tell whether this voxel is occupied. Another one tell whether it's empty or not. And there another one tell you whether this voxel need to be further partitioned, which they call mixed, this label. Here is the illustration of this concept. So this is a feature passing through, the 3D convolution passing through the network. So given a certain level of this octree, this is the feature map. They define a 1x1 by convolution. Essentially, it is the 3-dimensional or 3-way classifier to classify each voxel to 3 labels. So colored here. So the yellow one means that voxel is empty. The dark green ones means it's the field, means occupied. And the important one is this red one, they call mixed. This one need to be further partitioned into next level to generate more details about the 3D shapes, 3D shape. So for those pixels are labeled as mixed, they will pass through the feature map to the next level for further processing. So they can also apply 3D convolution on top of it, but they can save a lot of computation because they only need to apply 3D convolution on those so-called mixed features, mixed labeled features. So the experiment with single image based 3D reconstruction, from the left to right, of course, this is the input image. From left to right, they increase the resolution of a generative 3D shapes. We can see that more and more details are added when we increase the resolution from this octree-based generative network. Of course, there's one drawback that we can see there's more noise also added on the surface on the generated 3D shapes. But this is essentially I think the drawback of this volumetric representation itself instead of the network. So this also is very impressive result. Okay, that basically concludes my part of this lecture. We'll have a 15 minutes break, and then after that, and how we'll introduce irregular 3D deep learning. Thank you.
Hello, everyone. I'm Charles. I'd like to hold the microphone. All right, so in this session, we'll talk about deep learning technology for point cloud. both in point cloud analysis and also how to synthesize or generate point cloud from image or other data format. Actually, you'll find that we also mentioned this parametric models, which we can also consider that for generating normal point cloud is just X, Y, Z, or you can include RGB. But you can also generate point cloud with point, like with parameters. Like you can parameterize the point by, like you can have the box, you can have other primitives, and use those points with primitives to reconstruct a 3D shape. But anyway, the first part is the point cloud analysis. So this will be based on two of our recent works. One is the point net, which we also presented here in CVPR, and another one is point net plus. So it's like a hierarchical version on point net. It's like a point net v2, and it's on archive now. Okay, so the big motivation behind all of this work is that we observed that recently there are many emerging 3D applications. For example, for autonomous driving, you have LiDAR, a lot of LiDAR data. You want to do perception in the real environment. And also for augmented reality, you want to interact with the world. So you have 3D interaction. Then you need to understand this 3D environment. And usually the data is 3D point clouds, right? And also for shape analysis, you want to design shapes and deform shapes. You will deal with point cloud in many cases as well. So all these emerging 3D applications means a very strong need for 3D deep learning. And we argue that as you are already seeing, that there are many different 3D representations. We argue that point cloud among them is one of the very important one. Why? Because it's very close to the raw sensor data and fits well for the end-to-end learning idea for deep learning, right? So we know that you can get point cloud from LiDAR or from depth sensors. And also it's very canonical, right? So you can convert point cloud to other data format and also convert many other 3D representations to point cloud very easily, right? When you deal with point cloud, you feel it's like much easier than if you deal with meshes, right? Okay, so in our work, PointNet, we designed an end-to-end learning framework for scattered and unordered point data. So this is very different, and it seems one of the very first pioneer work to do deep learning on point cloud. Previously, it's mostly a handcrafted feature designed for different specific tasks. And our framework is a unified framework that can be adapted to various tasks, including object classification, object parse segmentation, or semantic scene parsing. Like what is shown here. Like you can classify point cloud instance into different semantic categories, or you can segment individual objects into different meaningful parts, like the leg of the table, or top of the table, or wings, engines, tails of an airplane, etc. And also you can do that in scene level. So you can segment a 3D scene, like here it's showing an indoor office, into different semantic regions, like the floors, ceilings, walls, or chairs, tables, etc. But one like obvious challenge we face to deal with point cloud is that this data is like in its data structure format is a set of vectors, right? We can represent this set by an array, which is like n points. Each point is d-dimensional. In simplest form, you can just include x, y, z, or RGB or normals. But this array is very special because we have orderless points, so we can arbitrarily switch the rows of this array, and they will represent exactly the same point cloud. So to deal with this data, our model has to be invariant to n factorial permutations of the rows of this array. So what function is invariant to those permutations? So we call this is like a symmetric function, right? For a symmetric function, you can have a permutation pi on all your data from x1 to xn, and you have whatever permutation you have, they should have exactly the same function value based on this set of points. Actually, you are very familiar with symmetric functions. Many functions, very simple function like max pooling, or average, or summation, or histogram, they are all symmetric functions. But you can imagine if you just apply this very simple symmetric function on your point cloud, you will lose basically all the information of a point cloud. It just get the centroid of the point, or just gets the maximum point, right? Doesn't make much sense for semantic tasks. So what we wonder is that how can we construct a family of symmetric functions by neural networks to make it rich in representation power? So the basic idea is that we can do that through a function composition. So we can compose a function by neural networks combined with a simple symmetric operation. So if you see here, like in this representation, if function g is symmetric, then the entire function is guaranteed to be symmetric. So you have the same function h for all your x. And if function g is symmetric, then this g function is symmetric, and after the gamma safe function, the entire function f is symmetric. So basically, if we have like x, y, z for each point, we can apply the same function h on each point to project the point basically to some hidden high-dimensional embedding space. And because this embedding space is like redundant and high dimension, then we can aggregate the embeddings from all the points through a simple symmetric function, say max. And then we will get a single embedding from all these n embeddings from each point, and we pass it through again to another like neural network gamma to get the global feature for our point cloud. So we call this architecture PointNet vanilla. So one following question to ask is that by constructing this function, what symmetric function family can we represent by this PointNet? Right? Can they represent enough family to make it meaningful for different tasks? So we have a very interesting finding that we can prove that this format of function can arbitrarily approximate any continuous set functions as long as you have enough neurons, right? But it's still like a very good news to set the foundations for this line of work. Empirically, we will use a simple multi-layer perception network as the function h, and also another one for the gamma. But note that the same h will be shared, so the weights are going to be shared across all the points to make the entire function symmetric. And we use max pooling. We also tried many other simple symmetric functions like average or weighted average. But empirically in our experiments, max pooling consistently works the best. In our multi-layer perception, it's basically fully connected layers with ReLUs and also batch normalization. Based on this PointNet vanilla architecture, we also adds on another module which we call input transformer network. So the idea is that you have an array of data, like endpoints with x, y, z as their coordinates, also as the feature for each point. We can predict a transformation based on this point cloud by a net called tnet. So this tnet is the input is point cloud, output is transformation, and itself is a PointNet vanilla. So it's also permutation invariant. And we will have this transformation, and the transformation will be applied on the point cloud. And we are trying to transform the point cloud to some canonical representation so that the model will be less affected by the rotations of point cloud. So rotations, anyway, it won't affect the class or the path segmentation of your object. We hope our network is going to be robust to that. So we want to add this transformation on the point cloud to align the point somehow. But that's the hope. Practically, we'll basically align the shapes to some canonical, certain, a few modalities of the orientations, like 90-degree difference, etc. But helps in performance for our network. So we add on that. This is actually very similar to a spatial transformer network in images, if you know. But one big difference is that since we operate on points, the transformation becomes really simple. It's just a matrix multiplication. So you no longer need those bilinear or trilinear interpolation anymore. So it's super fast and easy. To summarize this PointNet classification network from n by 3, so this is the simplest form, just have x, y, z. The endpoints with x, y, z input. We can first do an input transform to trying to align the point cloud to some canonical poles. And then we can use the shared neural network on each point to project the point into some embedding space with 64 dimensions for each point. We can apply a similar like transform on the feature space as well. And then we can again use some neural network to project the embedding 64 dimensional embedding to 1024 dimension, the final embedding for each point. And then we use this important max pooling function to aggregate information from all points to get a global feature vector for the entire point cloud. And then we can like have another few fully connected layers on the global feature vector to output scores for classification. So the entire system, including the transformer and also the embedding, the projection, are all learned end to end. So we can optimize our features for the tasks we are interested in. To extend this work to segmentation, so now we only have a global vector. It cannot be used for segmentation for the point. To extend that, we can simply do a concatenation between local embedding and global feature for each point, right? We just take down the embedding for a specific point from here to here, and then concatenate with the global feature together, so that now for each point we know both some the point itself and also the global feature. Based on that, we can classify each point into different categories. So it's a per point classification formulation. Also, look at some results. So even though this work is one of the first to try to use deep learning for point cloud, it's already achieving very promising results. For example, on this ModelNet 40 class shape classification benchmark, which I've also seen in previous talks, we are achieving this 89.2% accuracy, which is on par or even better than previous state-of-the-art on 3D CNNs. And also, we show results on part segmentation. So for the object, we can segment it into different semantic parts. On the left is output from partial input. So we have a 3D model, so we can use virtual scans to scan the shape so that we can get partial scans with missing holes, etc. The network can also perform on that. And on the right is segmentation output on complete point cloud. You can see that the result is basically very smooth. And number-wise, we also show that it outperforms previous state-of-the-art as the paper is published. So we compare with one based on traditional features, and also another baseline we built based on 3D CNNs. We also show results on semantic scene parsing. So giving an input point cloud, which is a fused scan from Matterport scanner of indoor offices, we can segment the point cloud into different semantic regions as shown here. The first row is the input, second row is the output. So it does a pretty good job on that as well. Right? Amazingly, actually, this is basically the output of our first run on this task. And as I saw this, I'm a bit surprised as well. We also show that our point net is very robust to data corruption. So in point cloud, you know that usually there are a lot of missing points in the data. You cannot get the points uniformly well everywhere and densely everywhere. So we show that if there are data missing, like from 0% missing data, so you have all the data here, and also if you miss 100%, yeah, we don't have a point here, so it would be 0. If you miss 95% of the point here, the accuracy would be like dropped a lot, right? But for point cloud, for our point net, you see that even you miss 50% of the point compared with your training cases, the accuracy drops by less than 2%. So it's very robust to the number of points you have, even though it never sees this number of points in training cases. And also, it's very robust to outlier points as well, and also to perturbations of point positions. So we also compared with 3D CNN. So both, now in this case, both PointNet and 3D CNN is like trained on complete 3D shapes. Like for 3D CNN, of course, you trained on complete voxels, and for PointNet, you trained on complete point clouds sampled from surfaces of 3D meshes. And at test time, we try to randomly drop out points and to see how the performance changes as we drop more and more points. You can see that the PointNet is very robust to that, while 3D CNN, the performance will decrease very quickly as you drop valid points or valid voxels. So why is PointNet so robust to those missing data? We try to understand that by visualizing what the network has learned. So the way we visualize is that we look at this global feature vector, which is the max pooled results from each point embeddings. We try to search back in the point to see which input points are contributing to the global feature. Because we have this max pool, we know that if the output of this point is very small, then this point will have no chance to contribute to the final global vector, right? So we know that which point would contribute, and we only keep those points as, we call this as a critical point set. And to visualize that, if we have some original shape represented by this colored point cloud to represent the depths for better visualization, if you visualize the critical point set, we see that it's a subset of the original point set, and it captures basically the contour and the skeleton of the original shape. And we can also see that which points won't affect the global feature vector. So we search in space, like by brute force search in a volumetric space to search for each point to see whether its output will affect. If you have this point, like embedding high dimension in space, if any of the output will be larger than the global feature vector, then it will affect the global feature vector, right? So we see which point won't affect those global vector. So if we visualize that, we call this points that won't affect the output as the upper bound set. So in this case, any point set that falls between this critical point set and the upper bound set will have exactly the same global feature vector. So you would have exactly the same classification result and scores. So by visualizing, we see that it's very robust because you can add on points or remove points, but as long as it's between these two sets, you would have the same result. Yeah. And it also generalizes well to all of sample categories. Like here, we visualize some shapes that are not included. Their category is not included in our training set. We see that we also have very reasonable skeleton capture and also very reasonable upper bound set. It means that the features we learned from this network is generalizable to unseen category and shapes as well. So PointNet is very good. It's a very simple architecture and a very effective on different tasks. It's like a uniform framework for many segmentation, classification, and also number-wise, it's performing really well on several benchmarks. But if we compare it with 3D CNN, we find that it's quite different because in 3D CNN, you have this hierarchical feature, you have multiple levels of abstraction. But in PointNet architecture, for example, in this simple illustration here, we have a very global feature learning. So you either have just embedding for one point, or you have a global vector for all of your points, right? So in this way, the local context feature is very weak in this architecture. Even though we can have a concatenation of local embedding and the global vector, but it's just the global and very, very local, right? We want to have something similar to 3D CNN of multi-level abstraction. So that's the work in PointNet++. So this lack of local context will actually result in some very real problem if we want to generalize the PointNet to a very large scene understanding. So for example, for this case, we want to do semantic segmentation for a table and a cup. But in the input, different from in PointNet. In PointNet, we will centralize, we'll make the data zero mean so that we have the point with the centroid as 0, 0, 0. But here we will randomly just translate the table anywhere in space. In that sense, the coordinates of the points will change so much that it's very hard for the network to generate as well. And also for instance segmentation, for example here, given a central point on the table, we want to know which point belongs to the same object as this point. So it will be, you would hope that it's like white for the entire table, but actually it seems to project the prediction to the chair as well because they are at the same height. So that creates some artifact for your segmentation. So why? Because in training you have all these different configurations of objects in space. It's like exponentially like different configurations. And if you only look at the global vector, it's very hard for you to summarize well for all kinds of different configurations. So the problem of only having a very like a single point feature or having a very global feature, and also they depend a lot on absolute coordinates, will make it very hard to generalize to unseen scene configurations in large scale, right? So our idea for this PointNet++, which is PointNet v2, is to use PointNet as a basic module and build a hierarchical learning framework, like applying PointNet in a recursive way to learn hierarchical features. So the idea is simple. Like in this image, it is like 2D illustration. There are some points scattered there. Like you have a PointNet in a local region to summarize the local region into a point. So the local region could include multiple points, right? And then you have a less number of points in your point set, and then you can do that recursively. If you look at the local region, then another issue comes out is that if you just look at a very small region, then sometimes you may only have like a very small number of points there. So for example, in the extreme case, you only have one point in that local region. Then you cannot trust at all to use your network to extract features for that. So we have to deal with this non-uniform sampling density problem if we want to have a hierarchical one, which look at the local region. So I will mention these two one by one, these 2 points. Yeah. So first, let's look at the hierarchical point set feature learning. So given an input point cloud, like here's the 2D example. So m points, each point has a coordinate which is d-dimensional. Here d is 2. Right. Also, each point can be equipped with a c-dimensional feature vector. For example, the RGB or intensity or normals, whatever you like or have in your data. So the first step is we can do a sampling of points, of regions we are interested in. So we do a furthest point sampling to select a subset of points. It's a little bit hard to visualize, to see here, but we select a subset of points from the original point set uniformly. And then we do a grouping to search neighborhood for each sampled centroid. We use a radius-based ball query. The query is based on the d-dimensional coordinates. So we query within a radius which points belong to this local region. And then we can use a shared small mini PointNet to summarize each local region into a feature vector, which is higher dimension, but represents the geometry and or the features in this local neighborhood. And as the output, we have n1 points, which is strictly smaller than n, and still we have the d-dimensional coordinates for each sampled point and a c1 dimensional feature for each local neighborhood. We will mention that for each local region extraction, we will use local coordinates rather than global coordinates. So that makes the network looking at more local region instead of the entire global point cloud. So we can apply this sampling and grouping like again and again, so that we can have multiple levels of abstraction for our point cloud. So in each level, we have a less number of points, but each point will capture a larger scale of local neighborhood. And to compare with the point net with the convolutional layer, we'll see that the input for the point net layer is like a small set of points in a local region, and they are orderless, and the neighborhood search is based on the ball query based on distance. But in convolution, like the input is a dense array of pixels or voxels, and you do convolution. The input is index ordered, so you have a well-defined order for your kernel. And also the neighborhood search is based on array. So array index, you have or Manhattan distance, if you like. And you have a fixed number of pixels or voxels in each neighborhood. So they are somehow similar, but very different in many aspects as well. So used for classification, if we have this abstract set of points, each representing a local neighborhood, we can apply another global point net again to summarize the entire set of points into a global vector, and then we can use a few fully connected layers to predict the scores for each class. We can also generalize this architecture to segmentation. So now we have so for segmentation, we'll assign a label for each point on the original point cloud, right? So for this intermediate set of points, we can copy it here at first, and then we can use interpolation to find out a feature in the point we care about from this level. Like, so for each point in this level, we'll use interpolation to find out its feature value, and then use a unit point net, which is basically a multi-layer perception on each point independently to update the feature vector. And also we use a skip link to connect the original levels features from these points to here, and then repeat it again so that we can get a feature vector for each point on the original point cloud. And then we can use this feature on original point cloud for point classification. So that summarized the first section. So we used hierarchical feature learning for point cloud feature for classification and segmentation. The second aspect we'll look at is the common issue of inconsistent sampling density. So we know that sampling density can vary a lot in 3D point cloud due to, for example, the perspective effect, and also the radial density variation or the motion of the sensor or objects, etc. So it's a very common problem. In CEN, we know that people have shown that using very small kernel has been working very well. For example, in VGG or ResNet, they all use 3x3 convolutions a lot. We asked the question, is it also true for point cloud learning? Actually, it's not. So if you look at this figure again, you will see that you will have different number of points in each local region. That's very different from image domain. You will have fixed 3x3, 9 pixels in each region. But for point cloud, since the density varies, sometimes you may only have 1 point, right? So by number, we can also show that if you decrease the number of points in your shape, like from 1,000 points to just 128 points in this chair, for example, the performance, if you look at the original point net, which is the green one, the blue one, which drops fine. But if you look at this yellow one, so that's the hierarchical feature learning point net plus, it drops so quickly that the accuracy drops a lot when you decrease the number of points. So, but what we expect is to deal with density by trusting regions with larger density, but do not trust regions with very low density of points. So if the local region has only like a few points, we want to look at a larger region so that we get more confidence on the patterns of point cloud. So by having that idea, we designed some new novel layer architecture. One we call multi-scale grouping. So instead of looking at only a single scale of local neighborhood, we look at different scales. Maybe like this is radius 1, and this is radius 2, then this is radius 4. So we have multiple scales of a neighborhood, and for each neighborhood, we'll use PointNet to extract features, and then we concatenate those features to have a concatenated feature for the entire neighborhood with different scales. And during training time, we can randomly drop out input points so that the network can learn when to charge the small neighborhood and when to use more for the larger neighborhood. Right? You can imagine if you drop points a lot, then it will have a larger weight, basically, for the larger neighborhood. But if you have a high density here, it may look more on the local neighborhood. And also another parallel design is to combine this local feature from different levels. So we know that we have a set abstraction different levels recursively apply, and we can also combine them from different levels. So this one is from level 1, this is from the previous level. So the idea is similar. So result-wise, we show that by adding this novel architecture to deal with this varying density problem, the performance is much better than before. If you like this, look at this red one as the green curve, we show that as the points misses, the performance nearly stays the same, even for like as less as point as 256. It's much better. So here we do this, show these results on ModelNet 40 classification results. There are like two conclusions for this table. One is that by using hierarchical feature learning, we see that PointNet++ is significantly better than original PointNet because it has a richer representation power by using hierarchical feature learning. And also, amazingly, we show that by adding normals, our PointNet++ can even be better than multi-view CNN-based method on classification. Without normal, like for some shapes like keyboard or like chairs with bars on the back, it's very hard to discriminate this with other categories. But with normals, it helps a lot for the performance, as we show here. And also, we show that number-wise, like by adding our novel novel layer to deal with the density problem, the accuracy on, so this is like a thing-level semantic segmentation task. So the yellow one shows the one with non-uniform point density. So without the novel layers, the performance drops a lot from the complete input. But with the novel loss, novel architecture, we can boost the performance by a lot. And also our architecture for hierarchical PointNet feature learning is much better than the original PointNet on this large scale scene segmentation task. Besides that, we also show that our PointNet++ is actually very flexible architecture. It's not restricted to Euclidean distance or rigid object. It can also be applied to organic objects. So for organic objects, for example, here we want to classify animals, but this horse and cat, even though they are very similar, if you just look at the contour and basic shape, they are actually different categories. But their pose is just very same. So for organic object project classification, we want to look at the surface and geodesic distance rather than the extrinsic shape. So the PointNet++ can be applied to that as well. If we use the coordinates rather than Euclidean coordinates, we can use geodesic distance-based distance and coordinates. And also we use the intrinsic features for each point. And evaluating on this benchmark, we get to the state-of-the-art performance on this. To visualize what the PointNet++ has learned, so we visualize the first layer feature where the model is trained on ModelNet 40 class, basically mostly furnitures. So we see there are some typical activation patterns. For example, the planes, the kernels or the poles or like a pole plus a plane, etc., which is common in furnitures. Okay, so I think in this first session, I covered PointNet, unified framework for deep learning on unordered point set, and also our extension based on PointNet, the second generation PointNet, PointNet++, which is hierarchical feature learning on point cloud, and also which deals with non-uniform sampling density in points. Next, I want to introduce Professor Liu Guibas, who will cover how to generate point cloud and how to do a primitive-based shape generation.
Okay, thank you, Charles. So I'll cover the final two topics of the point cloud session on point cloud synthesis and also on representing geometry through primitives. Before I start, let me re-emphasize one point in the material that Charles covered on PointNet and PointNet++. That is, this is not really specific to points in 3D. It can work with point sets in any dimension. For example, you can have regular points in 3D plus other attributes like RGB, or you can have physical information like stresses and strains. And in the end also, it can be done in any metric space. So one can use non-Euclidean metrics as well. Oh, the mic is... Oh, okay, sorry. I'm going to hold the mic closer to my mouth. Okay, so I'll talk first about point cloud synthesis. And the goal here is to solve a problem that was discussed already in this workshop by both Evangelos and Jimei, and also appeared several times in this conference, namely how to go from a single image of an object to a 3D version of the object. In some representation, we'll discuss the representations. And notice this is quite a challenging problem because in addition to inferring depth for every pixel that you see, you also have to imagine or to hallucinate the geometry of the part of the object that's occluded, that you don't see. And it's only possible because we have priors, because somehow we try to recover geometry that we have seen before in various contexts. In addition to the work here, of course, there's also evidence from nature that this problem is possible. For example, several birds, like pigeons, have their eyes on the side of the head, which means that the receptive fields of the two eyes overlap very little. The binocular area is very small. That means mostly they have to act based on information from a single eye. And even though we humans have stereo vision, we have two eyes, the baseline is very short. And we have no trouble understanding that certain objects that we see are the same, even though we see them from very different points of view. And again, this means somehow we are able to recover the 3D structure of the full shape from one or from two very close views. And it's interesting to think about what is the representation in the brain that makes this possible. But that's not the topic we'll address here. Instead, we'll try to solve it by algorithms in computer vision, and this is a problem that dates back to the early days of the field, to the seminal work by Berthold Horn at MIT on shape from shading, on understanding 3D structure from lighting. And this goes back more than 40 years now in computer vision. So, as you can imagine, we'll take a data-driven approach. That is, we'll try to say we have knowledge of objects in the world, and because we have knowledge of these objects, and because the shape of these objects is a set of measure 0 in a set of all potential shapes that could exist, we have a chance to be able to recover the shape of objects in images just from a single view. And we'll follow the paradigm of learning by creating synthetic training data. You already mentioned that we have various data sets now for 3D geometry. So in my group, we've been developing the ShapeNet repository that has about 2.5 to 3 million models. And given these models, we can generate renderings of them. We can generate images that we can make look fairly real by adding backgrounds, different lighting, occlusions, and so on. And now we have ground truth. We have images of objects, and we know what is the 3D geometry that generated this object. So we can use that to train a deep net. And the particular method that I will show you was based on training using roughly, I think, 220,000 shapes from 2,000 categories, and 10 million images were generated from that data. Okay, the question now is, in what format are we generate the 3D geometry? And this issue was already discussed extensively in the previous talks. And the sort of traditional candidate for deep learning is volumetric, because that is a regular structure that is easy for deep nets to consume or to produce. The trouble is that it's an expensive data structure, because the size of the grid is cubic in the dimension, and the result is, if you use a low res a cubic grid, you tend to lose fine detail. In most of the world, having thin legs is a plus, but in this case, it's a minus, because you lose them. Also, in the grid version, as was already mentioned, doing geometric transformations, like rotations, is quite expensive. So instead, as you might imagine, for being in this part of the presentation, we'll use a point-based approach. That is, the geometry that we generate is a point cloud. And in this case, we'll try to go from a single image of an object to a point cloud of roughly 1,024 points. And again, this is, I think, the first time that this type of approach has been described in the vision community. So here is what we want to do. We want to have an image of an object, say this car that you see on your right. We will segment this object, and then from that we will try to generate a point cloud in 3D space that captures the shape of the object. And I show here two renderings of this point cloud, one in the same pose as the object and the other from a different pose. So you can actually see that the reconstruction, the lifting from 2D to 3D, captures not just the front, but also the back. That is, it does infer part of the geometry that is not visible from the point of view from which the image was taken. And here's a comparison by mapping everything to volumetric grids to make it fair. So we start with an input table, and then we have our reconstructions using volumetric techniques, our reconstruction using a point cloud that was then converted to a voxel grid, and then ground truth. And you can see that we do better in capturing fine details, especially the legs of the table. Okay, let me discuss now the architecture of the network that accomplishes this upconversion, this conversion from the image domain to the 3D domain. And so we'll have a network that will be trained with ShapeNet data, and it will produce a point cloud. So of course, to train the network, we have to have ground truth. So we will take our 3D model in ShapeNet, whose view we're trying to upconvert, and also map it to a point cloud. Well, one thing to realize here is that the same shape can have multiple point cloud representations. It's not something canonical, like scan converting the shape onto a voxel grid. And so we have to have a somewhat nuanced way of comparing point clouds and defining the appropriate loss function. So let me say a few things about how to define this loss. Well, this is a geometric problem. We have two sets of points. The blue points, they're coming from the net, and the red points coming from the ground truth reconstruction, and we want to measure how close they are. And this is a non-trivial problem because we don't have associations between the points. We don't know which red point is supposed to correspond to which blue point. Well, there's various ways to solve this problem, this correspondence problem. And a classic method is to use some kind of assignment or transportation technique that tries to pair the points in such a way that you minimize the transport cost of the red point to the corresponding blue point. So basically you're trying to find a correspondence function phi that minimizes the sum of distances from, say, each red point to the corresponding blue point. And that's a classic optimal assignment type of method. And in my neck of the wood is called the earth mover's distance. Another way is to try to do something simpler, namely simply match each blue point to its nearest red point and vice versa. And this defines a variant called the Sanford distance. By the way, notice here we're using squares for the Sanford distance. This makes it easier to differentiate. But unfortunately, this makes it not a true distance. It doesn't satisfy the triangle inequality, but still we can use it as a loss function. So these are two possible distances, but one can think of others. And in this setting, we have to understand what are the relevant criteria for selecting a distance, which are the geometric criteria and the computational criteria. From the geometric criteria, we want the distance to reflect natural semantic similarity or difference of the shapes and to allow effective shape interpolations. At the same time, we want the distance to be differentiable and the computation to be fast because we have to do large-scale training. I want to point out that these distances are naturally differentiable, both the earth mover's distance and the Sanford distance, except for sets of measure zero. That is, as you start moving the points, there will be certain discrete instances when the associations change. But that set is a very, very small set in the space of all configurations of points. Now, another fundamental issue here is that since the net has to infer something that is ambiguous, something that has multiple solutions, there are many issues that come up because it looks like we're solving a regression problem, but we are not, because there can be multiple solutions. First of all, because there's a part of the object we don't see, so there can be many possible things hidden behind the front. But even in the part we can see, there can be ambiguities, because to be able to make the distance comparison meaningful, we're trying to generate a point cloud of the object in the same pose in space, in the same position and pose in space as the original shape. And sometimes there can be ambiguous views. There can be things that you think are pose A. So for example, you may think that the chair faces towards the front and to the right. But actually, it can also be facing towards the back and to the right. There can be some ambiguities. And both because of pose ambiguity and shape ambiguity, the tip net has really to deal with a distribution of solutions. It's not a function. It's not mapping one image to one shape, but it's mapping one image to a set of possibilities. And well, since the net doesn't know which one you want, it somehow tries to mix the solutions, and this creates problems. And here is a situation where the distance that you choose makes a big difference. So if you think of a distribution over shapes, for example, you take this circle of points and vary the radius. If you look at sort of the mean shape in terms of the earth mover's distance, you get a fairly nice and clean circle. If you do the same thing with the Sanford distance, well, you get a noisier version. On the other hand, if you start with something that has more combinatorial variation, for example, there is the center bars on the bottom and then these little noise outliers that show up, well, what happens with the earth mover's distance, it tries to smooth and clean up the solution, and it sort of merges the top and bottom outliers into mass in the middle. While in the Sanford distance, because you don't have to match one to one, you don't give so much weight to these outliers. So it's hard to tell which distance is best. You know, you can see from these real examples here that on the one hand, the EMD, when the shape is clean, gives you a cleaner solution than the Sanford distance. On the other hand, sometimes the same force can make the EMD lose fine structure that the Sanford distance can capture, as the bottom slide, as the bottom row shows. So we played with both. And now let me talk a bit about the actual structure of the network. One observation that is basic to the structure of the network is that the geometry on shapes, again, we represent the surface of the shapes or the volume, typically comes in two parts. There is a part that is smooth, like large areas that are planar, spherical, cylindrical, or quite smooth. And most man-made shapes have mostly such surfaces. But then there are also special areas like corners and things where the geometry becomes much more intricate. And somehow, if we're going to do reconstruction well, we must understand this distinction, because the statistics of these two types of geometry are quite different. So in fact, in the up conversion, when we're going to go from, because the network will have a standard convolver because it's an image. So we start in the standard way, we're going to have a standard convolutional architecture first. But then we'll do the up conversion, the lift into 3D through two different branches, one that captures the smooth behavior and one that captures the intricate behavior. And for the first, we'll use a convolutional approach, and in the other, we'll use a fully connected approach. And each of these will give us a point cloud, and then we will simply combine the 2 point clouds to get the final result. And here's an example of what happens with these two branches. Of the 1,024 points, we pre-allocate, I think, 768 to the smooth branch and 256 to the intricate or non-smooth branch. And here the smooth area is shown in blue in the reconstruction and the non-smooth in red. And you can see that the red captures sort of the edges, the extremes of the shape. And the up conversion branch is a fairly traditional convnet that ends up essentially computing a parametrization that is a map from a smooth surface like the plane up to 3 space. So basically, it produces x, y, z coordinates for points in the parameter domain, which in this case is just an array. And this is very good at capturing smooth shapes, as we know from traditional computer-aided geometric design. And the combination of these two things does quite well comparing to baseline reconstructions, especially compared to volumetric reconstruction. We get a 63% error reduction. So the moral here is the representation really matters. How you code your geometry can make a very, very big difference in the results that you get. And here I show some examples. Even though we trained the network with synthetic images, it can also work for real images. And I show some examples on top where you see the shape reconstructed in the original view and also from a different side. And on the bottom row, you see the network is able to do something even with shapes that are outside the categories that it was trained for. So it captures the basic structure of the shape. The same machinery can be used to reconstruct, not just from an image, but also from a partial scan. So it can be used to complete shapes. And this is just a beginning. I think that there is many, many open problems about understanding how to best select the appropriate loss function, the trade-offs between using the Sanford distance versus the F-mover's distance, how to add further structural constraints, for example, symmetries we may know about, how to do this beyond single objects. Right now, if you give this object if you give this pipeline a collection of objects, it will try to merge them into a single object, because that's the only thing that it's ever seen. And of course, we have to study more how generalizable the method is. Okay, and let me end by going to the last part that deals with describing geometry through primitives. This is really an old topic in computer vision, even older than shape from shading, going back to the early 70s work of Tom Binford at Stanford, who introduced the notion of representing 3D geometry by generalized cylinders. This is a simple geometric primitive that can very efficiently encode very common geometries. And the question now is, can we, given a 3D shape, can we find a representation of it in terms of a certain set of geometric primitives? And the primitives we use in this work, they're just the most basic possible. They're just boxes. So we take geometry, in this case we take geometry in voxel format, and try to replace it by these boxes that you see here. Furthermore, we would like these boxes to be allocated consistently across similar shapes. We would like somehow the boxes to capture some semantic information about the structure of the shape. And you see here the coloring is trying to show this consistency. So, as I mentioned, in this work, we start with a volumetric representation of the shape, and then we have an encoder, in this case, a traditional volumetric net, that tries to predict the primitives that we will have. In this case, we have just one primitive, and we start by something very simple, where we fix the number of primitives. I'll talk a bit later about how this restriction can be circumvented, but for now, say we are going to predict m primitives to describe the voxels that we see in the shape on the left. And the nice thing about this is that we don't really need supervision, because the geometry of the shape itself is the supervision. The question is that the geometry of the surface of the cuboids properly approximate the geometry that we started with. And each primitive explains some of the geometry. So now essentially, effectively, by computing these primitives that cover the geometry, we have also computed a segmentation of the geometry. That is, each primitive attracts or takes certain points as belonging to it, and therefore separates the voxels of the shape into different parts. And now, two interesting aspects here. One is how to deal with variable numbers of parts. Not every shape has the same number of parts. Some chairs don't have arms, for example. And one way to deal with that is to generate a certain probability for each part. That is, you say estimate m parts, but for each of them you give a probability that's actually present. So for parts that have very low probability, you can just truncate them off. Another interesting aspect here is the loss function is how well the geometry of the cuboids predicts the geometry of the shape in both directions. So you want essentially every voxel of the shape to be close to one of the primitives, and you want every piece of the primitive to be close to some part of the shape. Oops, sorry, I'm going the wrong way. And this shows this two-way Sanford distance again, where we measure distance from the cuboids to the voxel grid, and from the voxel grid back to the geometry. And we do that by essentially sampling points on the cuboids, and then measuring their distance to the original shape. And the nice thing here is that the coordinates of these points, they are all linear functions in the dimensions of the primitive, and therefore we have nice differentiability properties, so we can backprop in our net. And in fact, because the dimensionality of the representation is extremely low, that is one of the advantages of representing geometry by primitives, the number of independent parameters is very small, and this process can become quite fast. Another issue is the consistency of these decompositions. That is, we would like not just to parse each shape into primitives individually, but to parse them consistently. And what really helps here, I mean, this kind of falls out of the formulation, is that the whole pipeline essentially is a continuous function. So if the shape changes smoothly, the cuboid decomposition also deforms smoothly. And what this really means in practice is that if you have similar shapes, then corresponding structures, corresponding parts, very likely will be captured by corresponding cuboids. There will be an easy one-to-one correspondence between the cuboids of the shapes. So again, so what's nice here is that we are getting essentially a segmentation that is consistent across shape families, and we are doing that without supervision. Oops. This is simply a way to measure how well this method does compared to others, and here we can see that it actually outperforms by some other methods that are more classical in terms of the area of the faces of the primitives involved. And also we add a parsimony term in the optimization for the net, so that it tries to explain the geometry with as few primitives as possible. So you can see that initially it is using kind of more primitives, but as the iterations proceed, the number converges to what we would think of as a canonical explanation of the geometry of the shape. Once we have this machinery, and again, because we have ShapeNet models and we can get training data from ShapeNet, we can now start doing the same thing from images. Namely, we can take an image of an object and try to generate not a 3D model of the object in this cuboidal form. And again, this is only possible because we have this link between 2D and 3D coming from the synthetic data. Okay, so this is a very simple example of one primitive. I think one can easily consider variations where we add more primitives, we add spheres, cylinders, cones, other geometric primitives. These primitives can be very useful for modeling, right? Because once you have fit these geometric primitives to a shape, they all admit of natural deformation. So you can imagine elongating a cylinder, making a cube flatter, and so on. So I think this use for design is a very interesting possibility of this representation. I think a point cloud representation is not so great for design, but this is, because this gives you natural handles by which to modify the shape. And again, it'd be nice to automate this more like artists do. And I think this brings to the end of this presentation. So I covered two aspects here. I talked about how to go from a single image to a point cloud 3D version of the underlying object. And we saw several interesting issues in that part. The issue of the loss function, because now we don't have to, because now we don't compare regular structures like voxel grid, we compare point clouds. So we have to have distance functions that are semantically good, but also fast to compute and differentiable, so you can put them in end-to-end pipelines. We saw the issue of doing the up conversion through different paths, one meant to capture smooth geometry through parametrization, and the other through a fully connected ledger to capture the more, the more intricate aspects. We saw the issue of ambiguities and how to get a net to predict actually not one, but multiple structures. In fact, in the real implementation, there is something like a random variable that you can use to select among multiple reconstructions of the same image. So if you try it multiple times, you can get kind of different outputs that captures the possible variations of the reconstructions that you might want to have. In the second part, the main idea was to try to represent geometry through a very small number of simple geometric primitives. It was possible to accomplish that without training data, because essentially the geometry itself becomes its own supervision. And I think this is a very, very compact representation that we showed can be compact, across, can be consistent across related shapes, and provides a great tool for shape manipulation. Okay, thank you. break for 15 minutes? Okay.
So the original plan is to have the last session from 4:30, but I guess because we end a little bit earlier for the second session, we'll start at 4:20. Yeah, 20. So yeah, 15 minutes later, come back. See you.
Maybe would you like to conclude yourself, or
You can conclude, I guess. Yeah.
because I did the conclusion for my part, but I didn't add conclusions. Look, there are many. Of course, it's much sparser, but many people are still here.
Yes, I think actually I go around and find that basically our room has the most people compared among all the I'm glad that we're not losing audiences, so basically people stay here. This one, is double.
No, it's this one.
This one.
Yes. Just commented. So just check the last slide.
Last. Watermark. Yeah. Is it right? Yeah, is it right?
Yeah, let's check if the videos are working. I have videos here, so maybe I will present from my computer.
Okay, sure.
Where is .NET++ published? Is it?
It's a NIP submission.
Oh, it's NIPS.
Seems like it should be accepted.
Oh, good.
You need the pointer?
Yes, please.
USB. I think that this one has a lower voice, and you have to self louder.
Yeah, I will try.
Wearable thing. Where's
The wearable creates a lot of feedback. I have animations here. But why is the most So I think we need to start. It's already 4:20, so the sooner we start, the sooner we finish. And I feel really sorry that and guilty that I'm the last one to speak here, and I separate you from the beach or from your dinner, I guess. So basically, the last part of this tutorial, I would like to talk about, I would say a little bit exotic for, at least for this audience, kind of deep learning that we call intrinsic deep learning on manifolds. And this is a rather different way of thinking of doing deep learning or convolutional neural networks on 3D data. Basically, we'll not be considering 3D data as volumetric objects or as images, basically as Euclidean objects, vector space objects, but we'll be considering them as manifolds. This model is very common, I would say, very popular and very natural in computer graphics, and people dealing with geometry, I would say it is less common, and again, that's why I say that it's exotic in this community of computer vision, so hopefully it will be clear. And those of you who attended our tutorial in the first day about deep learning on graphs, you will find some similar concepts. So at the end, it looks more or less the same. Okay. So the main idea, basically, I think the main idea is illustrated well in this slide. If you look at this surface, this three-dimensional object that deforms, and here I will be talking mostly about applications that involve deformable shapes. Basically, we want to be invariant to deformations. For example, we want to find correspondence across different collections of shapes where we want to factor out all the deformations to be insensitive to these deformations. You will see that if we treat the object as a Euclidean object, as a volume or as a range image, of course we can apply the standard convolutional neural network as we've seen in the first parts of the tutorial, but basically the complexity of the network and the amount of training data will be pretty significant because we'll need to learn these invariance of these deformations from the data. The Euclidean neural network, at least in a straightforward way, will not be invariant to deformations, even not to rigid transformations like rotations. So basically the main idea of this part of the tutorial is to try to define the basic operations of convolutional neural networks, in particular the filters, intrinsically on the surface itself, in a way that the deformation invariance, at least a certain class of transformations that we call isometries, is automatically built into the neural network architecture. And as you will see, as a result, the networks will become much smaller. With smaller number of parameters, you will be able to represent basically everything that deviates from this isometric model, and as a result, also require much less training data. Okay, so that will be the main idea. The works I will be presenting, so I will basically presenting three classes of approaches: spectral methods that are based on the analogy of Fourier transform on manifolds, spatial methods that mostly result from the PhD of Davide Boscaini, who sits here, and embedding-based methods, which is more, I would say, recent class of approaches that actually will be presented at SIGGRAPH this year. Okay, so to start with the basics of our model, we model now shapes as manifolds. Basically, the only thing you need to know about manifolds that they don't have global Euclidean space structure. Basically, these are, technically speaking, topological spaces. You can locally model them as Euclidean spaces. This is what we call the tangent space, or for two-dimensional manifolds. For surfaces, this is what is called the tangent plane. So just don't be misled by the fact that these are two-dimensional manifolds. These are boundary surfaces of three-dimensional objects, three-dimensional volumes. Okay, but these are two-dimensional manifolds that model three-dimensional shapes. On the tangent space, we define an inner product that we call the Riemannian metric. It allows to locally measure angles and distances. And deformations of the surface that do not change the metric are called isometries, or metric preserving. Okay, and any property of the surface that can be expressed entirely in terms of the metric, and as a result will survive such deformations, all these properties are called intrinsic properties. Okay, we can also measure distances on surfaces, and these are called geodesics. Okay, basically shortest path connecting a pair of points on the manifold. Now we'll also be working with differential operators on manifolds, and again, without going into too much details, assume that you are given a function, some smooth function that lives on your manifold, what we call a scalar field. You can define a Hilbert space, basically a space of functions with an inner product on this manifold. And you can compute differential operators. In particular, we'll be interested in Laplacian operator, or in differential geometry, it's called the Laplace-Beltrami operator. It takes in a scalar field and spits out a scalar field. And basically, geometrically, what it does, it takes the local average around in infinitesimal neighborhood around the point and subtracts it from the value of the function at the point. Okay? Of course, accounting correctly for the local geometry, for the curvature of the manifold. What we like about the Laplacian is that it's intrinsic. So basically, everything that will be expressed in terms of properties and quantities derived from the Laplacian will be deformation invariant by construction. It is self-adjoint, or if you write it as a matrix, it's symmetric matrix. It has orthogonal eigenfunctions that will be interpreting as a generalization of the Fourier basis. And it's positive semi-definite, meaning that it has non-negative eigenvalues, which can be interpreted analogously to frequencies in classical harmonic analysis. Okay? So working with discrete shapes, we can discretize shapes, as you've seen in the beginning, in many different ways. For example, if we deal with point clouds, there are several discretizations of the Laplacian. We can basically build a nearest neighbor graph and assign weights that will depend on the Euclidean distance between the points. If we work with meshes, which is very popular representation in computer graphics, there is, I would say, ubiquitously used cotangent formula that basically looks at the average of the cotangents of the angle around triangles around each edge. Okay, so the bottom line, it boils down to a large sparse matrix on which you need to perform eigendecomposition. Okay, the eigenfunctions, again, as I said, are real and orthonormal. The eigenvalues are non-negative, and basically it boils down to this eigendecomposition problem of a large sparse matrix. Okay. So basically, you can interpret the Laplacian eigenvectors or Laplacian eigenfunctions as the smoothest orthogonal basis. Okay, basically, you can pose this eigendecomposition problem as minimization of what is called in physics the Dirichlet energy. Now, if we look at the Laplacian eigenfunctions in the Euclidean one-dimensional space, we'll find that these are basically sines or cosines, what we call the Fourier basis, right? You can easily see that if you take a cosine, take its second order derivative, you will get back the same cosine multiplied by the frequency squared, right? So these will be the eigenfunctions and the eigenvalues of the operator. And of course, we can generalize this idea by, instead of taking the standard Euclidean Laplacian operator, take the Laplacian operator on the manifold, and you will get orthogonal eigenfunctions that generalize the Fourier basis. Okay, so that's the main, will be the main idea of spectral analysis. Now, in the Euclidean case, you can take a function and decompose it into a linear combination of sinusoids of different frequency. Right, this is what we call Fourier analysis. So basically, the forward Fourier transform or the Fourier coefficients, nothing else but the projections of our function on this orthogonal basis. Okay, and the inverse Fourier transform is taking a weighted linear combination of the basis functions that are weighted by these Fourier coefficients. So the same idea applies to manifolds. We just need to replace the basis with the eigenbasis of the manifold Laplacian. Okay, and we can apply this to solve PDEs, for example. That's the simplest example of a PDE on a manifold, a heat equation. So basically what it encodes is what is called in physics the Newton's law of cooling. Here F represents the temperature at a spatial and temporal coordinate. And the Newton's law of cooling tells us that the rate of change of temperature of an object, which is the left-hand side, the temporal derivative, it's proportional to the difference between its own temperature and the temperature of the surrounding, which is differentially encoded by the Laplacian operator. And the proportion coefficient is called the thermal diffusivity constant. So on the manifold, it's exactly the same equation. The only thing that changes is here we use the manifold Laplacian, the Laplace-Beltrami operator. So we have the initial heat distribution, and basically as we allow for time to run, the initial heat distribution is somehow diffused on the manifold. So we can express the solution of the heat equation by applying what is called the heat operator, exponential of the Laplacian operator, where the exponentiation is understood in the operator sense. Basically, we need to apply it to the eigenvalues of the Laplacian. Okay, so what you see here is forward Fourier transform, right? We project the initial condition on the orthogonal basis. We take the exponentiated eigenvalues and we compute the inverse Fourier transform. Okay, so if I plug in the explicit expression for this inner product and I exchange integration and summation, what I get here is what is called the fundamental solution or the heat kernel of this diffusion equation, which is a function that depends on two coordinates, x and x prime, and also on the time parameter. Okay? So this is how heat kernels look like. They are centered around different points. So basically it tells you how the heat propagates from a point to all the rest of the points on the manifold. You see that it is geometry dependent. It's not shift invariant. At different points on the manifold, we will get different heat kernels. What is nice, though, that it is deformation invariant. You see that it follows the deformations of the horse. Now, this is the heat kernel. Let's see what happens in the Euclidean case, right? So if we, instead of the manifold, we assume that we are given a Euclidean space, and we plug in the orthogonal eigenbasis of the Laplacian, we see that because of the associativity of the exponential function, we get the heat kernel dependent on the difference between x and x prime and not a general function of x and x prime. And this integral is just a convolution of f0, the initial condition, of with the heat kernel. And this allows us to interpret in terms of signal processing. We can actually interpret the heat kernel as the impulse response function. Basically, it's how if we initialize our heat diffusion equation with the delta function, how it will look like after time t. Okay. Now, remember what is a convolution in the Euclidean case? It's given by this convolution integral. Basically, it's a shift invariant operation, meaning that if I shift one of the functions, the result will be the same result shifted. It commutes with the Laplacian, so basically it is diagonalized by the same eigenbasis. And this is what is called the convolution theorem. Basically, the Fourier transform diagonalizes the convolution operator. This is bread and butter of classical signal processing. It allows to do filtering in the spectral domain. The way we do it, we take the Fourier transform of signal f, we multiply it by the filter, denoted here by g hat, and we compute the inverse Fourier transform. Okay? And why it is good? Because in the Euclidean case, we can compute the Fourier transform fast using the f of t algorithm. Okay, so again, let's write it for matrices and vectors. Basically, the convolution, if we write it as a matrix operation, is expressed by this matrix that has a special structure. So the coefficients of the filter form the diagonal of this matrix. This is what we call the Toplitzner circulant matrix, and it's, as we said before, diagonalized by the Fourier in the Fourier basis. So we can write it like this. This is in matrix vector notation the Fourier transform of f. Multiplying it by diagonal matrix means pointwise multiplication, and this is the inverse Fourier transform. Okay, so this is the discrete version of the Fourier convolution theorem. Unfortunately, in the non-Euclidean case on manifolds, we don't have any shift invariance, so we cannot even define, or at least not straightforwardly define the convolution integral, but we can take what is a property in the Euclidean case, the convolution theorem, and say this is our definition of what we can call the spectral convolution, right? So we define the convolution as taking the Fourier transform of f, taking the Fourier transform of g, multiplying them element-wise, and taking the inverse Fourier transform. Okay? Or in matrix notation, we can write it like this. Basically, Fourier transform of f, multiplication by the diagonal matrix of spectral coefficients, inverse Fourier transform. Okay? And this matrix G is no more circulant. Basically, the result is not shift invariant. What is worse, that the filter coefficients depend on the basis. Unlike the Euclidean case where the basis is fixed, it's the property of the space in which we are working. Here, each manifold, each shape comes with its own Laplacian, with its own basis. We'll see why it is a problem. Okay? So let's now fast forward to the generalization of convolutional neural networks. Basically, we'll start with the spectral domain representation, and we would like to formulate the convolution operation in the spectral domain. And basically, this is a work of Joan Bruna. They were the first to do it on graphs, basically a convolutional model on graphs. And the idea is exactly the same convolutional layer that we have in the classical case, in the image analysis, for example, but the filters are represented now in the frequency domain. So the way it works, you take your function, you compute the Fourier transform on the manifold or on the graph, you multiply it by these diagonal matrix of the spectral coefficients of the filter, take the inverse Fourier transform, and basically you can do it with multiple filters, and this C denotes here a nonlinearity, for example, the half rectifier. Okay, so this was the first conceptually important work. Actually, it has many disadvantages. For example, the number of parameters here is order of n, the size of the input, number of vertices in this case, in the mesh. And in classical convolutional neural networks, the number of parameters is fixed. It's independent on the input size. Also, the complexity of the computation is order of n squared, because we don't have FFT on manifolds or on graphs. Basically, you need to multiply by this dense matrix of eigenfunctions. There is no guarantee of spatial localization of filters, which is also one of the nice properties of classical convolutional neural networks, that the filters are local. Here, the filters are not necessarily local, they can be anything. And what is worse, that the filters are basis dependent. Basically, it means that if we learn a model on one shape, we cannot apply it immediately on another shape. We will see how to, at least to some extent, remedy this problem with spectral transformer networks. Okay, so to give you an illustration of this problem, this is a function that is given on a horse. Okay, so some blobs. Okay, I design a filter that does some kind of edge detection. Okay, I compute it in the Fourier basis of this horse, phi. Okay, now let's start deforming the horse, and we'll be using exactly the same filter in exactly the same function. You see that the result is totally different. And the reason is that the basis is unstable. Basically, each deformation of the horse will have a new basis that is not necessarily consistent with the basis of the original shape. You can see it here. This is the 50th eigenfunction of the Laplacian. You see that it changes completely across different poses. And these are almost isometric deformations. So if we consider non-isometric deformations, it will be totally different. Okay? So we'll see again how to remedy this property with spectral transformer networks and with spatial construction of convolution in the following. But let's go back to the second problem that we had, the lack of spatial localization. Okay? So basically that was again one of the fundamental properties of classical convolutional neural networks. So basically what we want to do, we can express the localization property in the frequency domain. Basically, what should the spectral multipliers of the filter satisfy in order that in the spatial domain on the manifold, the resulting filter will be localized. Okay? And we can use, in the Euclidean case, we can use this property of the Fourier transform that basically in signal processing is called the vanishing moment property. Right? Basically, if we want the moments, higher order moments of our function in the spatial domain to be small, we want the higher order derivatives of the Fourier transform to be small. Basically, the bottom line is that localization in space translates into smoothness in the frequency domain. Basically, what we can do, we can parameterize the filter using a smooth spectral transfer function. And if we make it parametric, we can also make the number of parameters that express the filter independent of the input size. Okay? For example, we can use polynomials, or if we want to be completely correct, it's better to use Chebyshev polynomials because that's an orthogonal basis. But without going into these details, basically we can consider a class of polynomial spectral transfer functions that are smooth by definition. Okay, and basically here, everything, all the problems that we've seen before are solved. The number of parameters is fixed. The filters actually are localized. Not only that they're localized, they have guaranteed R-hop support, because here we are taking R's powers of the Laplacian, and the Laplacian is a local operator, so it affects only one ring on the graph or on the mesh. We don't have any explicit computation of the eigenvectors. Basically, it boils down to applying powers of the Laplacian to our signal. So this leads to linear complexity in the input size. Again, we don't have generalization across domains. So this deficiency still remains. Okay, and again, why we don't have generalization across different domains? Because the eigenvectors, especially the high frequency, on different shapes behaves differently. You can see here, for example, the 20th eigenvector of the Laplacian looks very different. Okay, so basically, I don't have time to go into details, but basically what we can do is, if we have correspondence between the two shapes, x and y, we can express it as a linear operator, what we call the functional map. That was also work from the Sanford group. And if each of the function that lives on these manifolds can be expressed in the Fourier basis, let's say I truncated at k first coefficients, basically we can approximate this linear operator in the frequency domain, basically as a low rank operator, and then we have a matrix C that translates Fourier coefficients from one basis to another basis, encoding these correspondence. So this matrix will usually look like this. Ideally, in the ideal world, it will be diagonal, because if we expect the shapes to be isometric, their eigenfunctions will be the same, maybe up to sign. In practice, because the shapes are non-isometric, it will have this funnel shape structure, because at high frequencies, the eigenvectors behave differently. Okay? So basically, this matrix C encodes the correspondence between shapes in the frequency domain. Okay? Now, if we write the correspondence operator like this, as phi transpose C transpose Psi, basically we can think of this phi C transpose as a new basis function. Okay, so let's call it phi hat or phi bar. Okay, so basically in this new basis, you see that the functional correspondence is encoded by the identity matrix. So basically, you can think of functional map as a kind of synchronization of the basis. So I am finding a new basis, I'm modifying it by means of linear transformation, such that the Fourier coefficients, the new Fourier coefficients in this new basis, speak in the same language. Okay? And again, going back to spectral convolutions, if I take a spectral filter that looks like this, I apply it to my two different shapes, I get completely different results, right? Because the bases behave inconsistently. So the idea of spectral transformer networks is to use some intermediate shapes, let's call it this gray shape shown here in gray. Basically, we want to do the filtering in the common basis of this shape by means of these functional maps. And you see that in this new basis, the filter is now behave consistently. Okay, so if this was the structure of the spectral convolutional neural network we've seen before, basically we took a signal, computed its Fourier transform on the manifold, applied the spectral filter, and computed the inverse Fourier transform, maybe followed by nonlinearity. Here we introduce the spectral transformer module that modifies the basis, like in classical spatial transformer networks introduced by the group of Zisserman. Here this transformation is applied in the spectral domain, in the k-dimensional space of population eigenvectors. Okay, so that was a work again from the Stanford group that was presented where actually here at this conference a few days ago, and basically it solves the problem of lack of generalization across of different domains. Of course, now you need to explicitly compute the Fourier transform, and this comes at basically at high computational complexity, because you cannot compute it in n log n operation. You need n squared operations. So here are some results. So this is examples of normal prediction with spectral transformer networks, and you can see that it works very nicely. Basically, here the color represents the orientation of the normal. This is another example of shape segmentation, similar to the problems that were shown in the first parts of the tutorial, where if you compare to the ground truth, the segmentation is very faithful. Okay, so that was about spectral domain methods for doing convolutional neural networks. Let's now move to the spatial domain methods. So basically, if we look at different possible definitions of the convolution, we've seen in the Euclidean case the spatial domain, right? Basically, we can think of convolution as applying some kind of a template and running it over a signal. Okay, so that was the convolution integral. In the spectral domain, we've seen the convolution theorem, and the spectral CNNs were based on this analogy that was performed on the manifold. So the question is, what would be the spatial equivalent of convolution on the manifold? Okay, and again, think of convolution as a kind of page-based operation. In an image, you extract a page of pixels, you multiply it by some template, right, your filter, you sum up the result, and you move to a next position. So we'd like to generalize the same thing on manifolds. The only thing that will change now is that this page will be position dependent. We don't have any shift invariance. Okay? So technically speaking, we can define a local system of coordinates in which we represent the function that lives on the manifold locally around the point. Okay? And we call this a patch operator. And again, if in the image the very way that the page is extracted is position independent because of shift invariance of the underlying space, here it is position dependent. The extraction of the page at point x and x prime will be different. Okay. A different way of thinking of the page operator is by applying some weighting function to the function that lives on the manifold around the point, and basically representing the local system of coordinates as local averages of the function. Okay. And we can define the spatial convolution with a filter in this way. Basically, we take the local page multiplied by our filter and sum everything up. Okay. So this can be a continuous filter or can be discrete filter, basically whether our family of weighting functions is continuous or discrete. In practice, of course, it will always be discrete. Okay, so this is probably the most intuitive and the most straightforward way of defining these pages. So we can use local geodesic polar coordinates. Basically, the page will look like a radial page here, but it will be defined intrinsically on the manifold. Okay, so the weights here will be radial and angular weights that will localize, basically will average the values of the function in each of these radial and angular bins around each point. Okay, so if we plot the local polar system of coordinates in a plane, these will be the, for example, the weighting kernels that are used for these geodesic patches. Okay, and we define the geodesic convolution in this way. So it is illustrated here. This is a patch extracted around a point, and we multiply it by the filter G. So you can already notice a problem with this definition, and the problem is that we have rotation ambiguity, right? We can rotate the filter by some delta t, and basically there is no clear way, or at least not immediately clear way, which of these orientations to choose. So there are several solutions to this problem. First of all, we can choose some canonical orientation. For example, we can use some the maximum curvature direction, as we'll see in the following. We can also take the angular coordinate and take the standard Euclidean one-dimensional Fourier transform with respect to this coordinate, and this will translate the rotation ambiguity into a complex phase. And if we take the absolute value of the Fourier transform, we get rid of the phase and we make it rotation invariant. The third possibility would be to keep all the rotations, and we call this angular max pooling. Basically, we extract the page operation, we apply the filter, so it's like correlation with a rotating mask, with a rotating template, and then at the end we take the maximum. So actually there was a paper from Duke and this conference where they used the same idea for images. We did it 2 years ago for manifolds. Okay, and this is how we express the convolutional layer in the spatial domain using these geodesic patches. So we use this angular max pooling to solve the rotational ambiguity. It gives us directional filters that are also spatially localized. The number of parameters is fixed, and all the operations are local. So in principle, it's order of n computational complexity. Of course, the angular max pooling potentially reduces the discriminativity of this approach. Okay, so here's an example what we can do. Basically, this generalizes the convolution, so you can build any arbitrarily complex convolutional neural networks that work intrinsically on the manifold. Let me show you an example how we can use this kind of architecture for learning optimal local descriptors. As you know, basically, at least before deep learning, there was a plethora of different local descriptors, both for images and for geometric data, that try to describe local structure of the manifold around the point. So here, assume that we are given two shapes. Basically, we construct a Siamese architecture where there are two identical replicas of the same neural network with shared parameters, and they produce at each point feature vectors, f and g. And if we have a training set with shapes with known correspondence between some points, so here corresponding points are represented by the same color, we want these features at the corresponding points to be as similar as possible, and at non-corresponding points to be as dissimilar as possible. Okay, and basically by minimizing this loss, we try to make these as discriminative as possible descriptors. So this is how it looks like. So what I show here is the distance in the descriptor space from the white point here on the shoulder to all the rest of the points on these and other shapes. And cold colors mean that the distance is small. So this is HKS, again, work from the Stanford group, which is basically a diagonal of the heat kernel. You can think of it as a kind of multi-scale Gaussian curvature. So this descriptor, you can think of it as a low-pass filter. It is very smooth. If I move away from my point, the descriptor will change very little. Okay, and you see, in fact, that its localization is pretty poor in this example. This is wave kernel signature. That's a work from the group of Daniel Kremeres. So it's based on the different formalism of coming from quantum mechanics. So you see that this descriptor is much better localized, but it's less discriminative. For example, points on the belly of this human, for some reason, look similarly to the points on the shoulder here. Okay, and this is how the features produced by geodesic convolutional neural network look like. Way better than the handcrafted descriptors, and indeed, you can look at these curves. So these are different evaluations of the descriptors. Basically, the bottom line is the higher the curve is, the better the quality of the descriptor. It significantly outperforms some standard handcrafted feature descriptors. Okay, so that was the construction of that we call geodesic convolutional neural networks. Let's now look at a different way of constructing these local page operators. And for this purpose, we'll consider again heat diffusion on manifolds. We've seen this diffusion equation, right? Where basically the diffusion constant was assumed to be fixed everywhere on the manifold. So the heat conductivity properties of the surface were equal at each point. We want to consider different kind of diffusion where these diffusion properties are not only position dependent but also orientation dependent, what we call anisotropic diffusion. Okay, so here you can see an example of a difference between isotropic and anisotropic diffusion. So isotropic diffusion propagates heat equally in all directions. Anisotropic diffusion propagates heat differently in some preferred direction. And what is important, this construction can be made intrinsic. So basically, if I deform the shape, it will follow the deformations of the shape. Okay, so again, without going into too much technical details, the particular class of anisotropic diffusion tensors that we consider here are rotation matrices and some scale. Basically, what it does, it allows to define as a Laplacian operator that now has two extra parameters. Theta is the orientation with respect to some canonical direction. You can use the principal curvature direction. Well, strictly speaking, that's not intrinsic, but you can use any smooth or piecewise smooth vector field defined on the manifold. And alpha will be an elongation, basically telling how anisotropic this diffusion will be. Okay, and we can define heat kernels as before. And basically now the heat kernel has three parameters. It has the scale, basically the size of the blob, the orientation, and the elongation. Okay, and we use these anisotropic heat kernels as weighting functions for our page operators. Okay, and basically this allows us to define basically local pitches, as we've seen before with geodesic convolutional neural networks. Again, these filters are directional, spatially localized, and only order of 1 parameters per layer. Unfortunately, the computation of the heat kernels, at least the way that we did them in the paper, is expensive, because we also need to account for many different orientations. Okay, and again, that was the example of the descriptors that we've seen before with geodesic convolutional neural network. Here we see even better results. What is also important to notice that these kind of pitches, because intrinsic symmetries flip the orientation of the page, they allow to automatically differentiate between symmetric points on the shapes, which intrinsic descriptors like heat kernel signatures do not. Okay, so back again to the construction of the page operator. The next step you can do is to make this operator learnable, and that was the paper that we presented in this conference. Basically, if we construct a local system of coordinates around a point, we can create a parametric family of weighting functions called them W, depending on some set of parameters theta, and we apply this family of weighting functions to our local coordinates. For example, we can, for simplicity, consider Gaussians that are parameterized by the mean vector and the covariance matrix. Okay, So this is how it looks like. Basically, again, consider the same geodesic polar system of coordinates, rho and theta. We apply the Gaussian weighting functions in these coordinates, and the spatial convolution will look like this. So if I now exchange the position of the integral in the sum, what we get here is a Gaussian mixture. So basically, that's why we call these convolutional neural network architecture mixture model network, or MONET for short. And basically here we have an additional degree of freedom, a learnable patch operator. In images, of course, it will be superfluous, because you can already absorb these degrees of freedom in the filter itself. Here we have both learnable patches and learnable template coefficients. Okay. And if you compare it to the previous two models, the geodesic CNN and anisotropic CNN, basically there we had fixed patch operator with fixed weighting functions. Here we allow to adjust the weighting functions in an optimal way. And it produces much better results. We can actually show that it generalizes many previous convolutional or convolution-like neural networks, including, of course, the classical CNNs, also many models that are used for deep learning on graphs. But we covered that in the first tutorial, in the first day. Okay, so let me show you how we use these kind of architectures to learn deformation invariant correspondence between shapes, which was one of the motivating examples for these kind of applications. Okay, so there are several ways of computing correspondence. Of course, you can use local descriptors, just match them and find the nearest neighbors, and maybe do some post-processing. A different way would be to say that we consider correspondence problem as learning, as labeling. Okay, so assume that we are given some reference shape. We take a point x on our query shape, and we design a deep neural network that produces an output vector that has the dimensionality of the number of vertices in the reference shape. Okay, so I am using reference shape just for convenience. It's just label space. Okay, and the output can be interpreted as a probability distribution of basically probability of point x corresponding to a point y on the reference shape. Okay, and basically we can find the optimal parameters of the network by minimizing cross entropy or logistic regression costs. That basically the distance between the ground truth correspondence distribution at delta at the ground truth point and the output produced by the neural network. Okay, so ideally we want both to be deltas at the same location. Now, how we evaluate the quality of the correspondence, basically given a ground truth correspondence and the correspondence that we obtain from the network, we measure the geodesic distance between these points, and we average it over all the points. This is the protocol that is used in the Princeton benchmark that Leo mentioned in his part of the tutorial. Okay, so basically in the Princeton benchmark, we measure the percentage of correspondences that fall within certain error radius around the ground truth. Okay, and we get these curves. So just to calibrate the expectations, the yellow curve shows blended intrinsic maps, one of the state-of-the-art methods used in computer graphics that doesn't use any learning. The green curve shows random forest, one of the first methods used that are learning-based for finding correspondence. This is geodesic CNN. This is anisotropic CNN. This is what we get with MONET. So you can notice here that about 90% of correspondences have zero geodesic error. Means that they're perfect. Okay, and basically the maximum error roughly is about 4 centimeters, which is more or less the size of the human finger. So maybe to better appreciate it, what we plot here is the local correspondence error, the deviation from the ground truth correspondence. Here it's calibrated in centimeters. So these are blended intrinsic maps. If you look at the correspondence produced by blended intrinsic maps, it looks nice because it's very smooth, but actually it is not. It's pretty bad. This is what we produce with geodesic CNNs. You see that many points have zero or a very small correspondence error. Of course, there are some sparse points where the correspondence error is pretty large. This is what is produced by anisotropic CNNs, way better. And this is what we produce with MONET. So here the correspondence is nearly perfect. It is better to visualize it by texture mapping. We take the reference shape and we transfer from it this checkerboard texture to different versions of the shapes. And you see that there are some distortions, some artifacts, but they're almost unnoticeable. Here are some more challenging settings. Here we have range maps. So basically these shapes have different topology, some missing parts, invisible parts. And again, here the correspondence is pretty good. And some more examples of pretty extreme partial correspondence. Okay, so let's again look at the formulation of correspondence as a classification problem. Basically, if we consider correspondence as a classification, basically we throw away some important geometric information. Namely, look at this example. Let's say that the gray is our ground truth. If I have two correspondences, the blue one and the green one, which one is better? Obviously the blue one, right? Because it is closer to the ground truth in terms of geodesic distance. But in terms of classification cost, if I didn't hit exactly the ground truth correspondence, it means that I misclassified, right? So it doesn't account for the correctly for the geodesic distance. Also, the output of the network is not a pointwise correspondence, it's some probability distribution. So basically the more correct way of measuring the correspondence error will be soft correspondence error. Basically we take the geodesic distance, we weight it by the probability of x corresponding to y, and we integrate it on the reference shape. Okay? Now, another deficiency is that in training time, by minimizing this cost, we can guarantee that two nearby points will be mapped to nearby points on the target shape. We cannot do it during the test time, during the inference, right? Nothing in the world guarantees it. Basically, it's a point-wise operation. The correspondence is predicted at each point of the query shape. That's exactly the structured output, or what is called in computer vision the structured prediction problem, right? For example, when you label pixels in images, you want to condition the output of the network in one pixel on what happens in your neighborhood, right? So exactly the same thing happens here. We want to somehow produce structured output, because correspondence is not just point-wise property. It depends on what happens around it. And again, we'll use here functional maps. Basically, what we've seen in spectral transformer networks, we can describe correspondence between two shapes by a linear operator and express it in the frequency domain as a transformation of the Fourier coefficients. And if we have many corresponding functions, let's say some local features that, as we'll see in a second, will be produced by our convolutional neural network, basically we can build a linear system of equations and find C from this linear system of equations. Basically, a compact representation of the correspondence. Now, if we interpret and basically this is just solving linear system of equations, solving it in least squares sense. Now, if we again look at the functional correspondence in the spatial domain, basically because we truncate the Fourier basis, it will map a delta function to some blob. This blob is not necessarily positive, actually, because of truncation will have what is known in harmonic analysis as Gibbs phenomena. It will usually have some oscillating side lobes, right? So if we take the absolute value of this thing and normalize it, we get a probability distribution, right? So basically, we get the soft correspondence of a point on the reference shape, and instead of learning point-wise descriptors as we've seen before, we can actually do something more complicated. So the neural network will learn local features as we did before, right? But instead of comparing these features and learning point-wise descriptors, we'll project them onto the Fourier basis, right? We'll compute the functional correspondence C. From the functional correspondence C, we'll produce the probability distribution, and that probability distribution will be used to compute the soft correspondence error, okay? And this will be the cost that we'll be minimizing. So this is a fixed layer. We need to backpropagate through the functional correspondence. Fortunately, it has a closed form expression. Basically, we need to backpropagate through this pseudo-inverse. And basically, you can consider it as a complicated way of measuring the cost, the quality of the correspondence. And if we were happy with the performance of mixture model network, this is how the functional map network works. So basically, the Faust benchmark on which we were testing is already saturated. It's almost perfect correspondence. This paper is not published yet. It was just accepted to ICCV. Okay, so in the remaining time, let me cover briefly a different class of approaches that use some embedding space to define the convolution. Okay, and basically the idea is to use some kind of global parametrization to map the shape into some parametric domain which has shift invariant structure. Okay, And it allows to use, in that space, to use standard convolutional neural network. Basically, you pull back the convolution from that space. You may, by construction, guarantee invariance to some classes of transformations. The deficiency of at least the approaches that I'm aware of is that this parametrization is usually non-unique. Okay, and usually this embedding will introduce distortions. So basically, one of the things that we lost when we moved from the Euclidean space to the non-Euclidean setting was shift invariance, right? So let's think again, what is translation invariant? How can we define translation invariance on a manifold, or how we can define translation on a manifold? Basically, you can think of it as some locally Euclidean translation, or in other words, flow along a non-vanishing vector field. Basically, I move infinitesimally each point on the manifold in the tangent space by means of a vector field. Unfortunately, what we know from a result in differential geometry that is called the Poincare-Hopf theorem, that the only possibility for constructing such a vector field is on surfaces which have genus 1. Basically, they look like a torus. In maybe in more practical setting, this is called the hairy-ball theorem. Basically, it tells you if you have a sphere with hairs, you cannot comb it without introducing singularities. But you can comb a torus. Okay? So basically, on a torus, you can have shift invariant structure. That's actually the only two-dimensional manifold on which you have this kind of shift invariant structure. And basically, the idea, this is the work of from the group of Jeroen Lippmann from Weizmann that will be presented at SIGGRAPH this year, next week. Basically, they use an embedding into the torus. The embedding into the torus is not uniquely defined. It's determined by selecting a triplet of points on the surface. Each triplet of points produces a different embedding, and then the convolution is brought back from the torus to the surface. You see actually that it distorts its conformal map, but it scales locally the area, and different selection of these triplets will produce different local scaling. So you can consider it as an advantage. Basically, it allows you to zoom in onto some regions of the manifold. But the problem is that different selection of these triplets gives you different results. So what they do is basically they consider multiple selections of these triplets and then do some kind of folding, aggregate the results. Probably a smarter way of doing it would be some kind of spatial transformer networks where you basically optimize for the best position of these triplets of points inside the network itself, like spatial transformer networks do. Okay, and it produces pretty nice results in shape segmentation. I'm not sure that it's comparable to the results that we've seen before, but I think it's a nice animal in this zoo of intrinsic convolutional neural networks on manifolds. Okay, so to conclude, basically, intrinsic deep learning allows architectures that are deformation invariant by construction. So this is what distinguishes them from the volumetric or image-based or point cloud-based approaches. This, in turn, in applications of deformable correspondence, for example, implies that we'll need much less parameters and much less training data. So the examples of correspondence I showed you were trained on 80 shapes. So by any standard of deep learning, this is an incredibly tiny training set. So to achieve similar results with Euclidean methods, you would, for example, recent work of Hao Li from last CVPR use 50 million training examples. So I think it's uncomparable in terms of the training set size. It's part of a bigger trend of what we call geometric deep learning, basically deep learning on, especially on graphs. And there are several ways of defining intrinsic convolutions. Each has its own advantages and disadvantages. Shape synthesis in this case is a very big problem. So we have some ideas how to do it, but I think so far it has not been done. Okay, so that's all. Thank you very much for listening, for remaining so late. And I guess if you have questions, we'll be glad to answer.
And also, I want to announce that for the material of this tutorial is already online. It's on the website. Okay, So for the CVPR 2017 booklet, there's the tutorial, and there also shows the website of our tutorial. Yeah, the slides are all there. 3ddl.stanford.edu, I think that's it.